So welcome to the second day of KVM Forum. I'm going to open very quickly with the Qemu status report for this year, and then we can split again the two rooms. I will start with some highlights about various parts of Qemu and various kind of changes that happened this year. For accelerators, we removed hex, nomen omen, as you say sometimes. Like Hex was a hypervisor that Intel developed for the Android emulator. It went unmaintained since Windows got support for WHPX a few years ago, and we just removed it from Qemu as well. TCG plugin support was brought onto Windows. The only problem was just basically build system stuff, so there was nothing that was really blocking the plugins from working. For KVM, we have some nice changes. Xenon KVM support is way more complete and basically usable. VSMP support is the first big full-blown implementation of constitutional computing for x86. It was some nice work done in collaboration between Intel folks for TDX and AMD folks for SMP. And also we have a new architecture, which is Long Arch. It's been supporting TCG for a while, both as a host and a guest. And now we have also KVM support. For the build system, Jon Snow and I had this pet project of having a Python virtual environment so that everything that uses Python during the build use just one Python interpreter. This makes it easier to use newer Pythons on CentOS 8 and /15. CentOS 8 is actually not anymore a supported build OS, but it actually works. Like, it's just that we don't support it. And also we upgraded to Python 3.8. Also in the build system, we have automatic dependency download. Right now we have two kinds from pip, from the Python package index, and also for Meson subprojects where libraries like libfdt and libslurp now are not anymore submodules, they switch to Meson subprojects. And also, spoiler alert, this might be extended in the future to Rust crates. And finally, we have an interesting change to run functional tests without Avocado. It's a new thing, so I'm not super up to speed with it. I'm not sure whether you can still run them with Avocado, but anyway, this makes it easier for developers to run the functional tests for some kinds of changes, for example, Xenon KVM changes. We had a lot of changes from our retro computing fans. 68K can run a bunch of operating systems, including macOS and Apple Unix, and more modern ones like NetBSD and Linux. HP PA RISC got 64-bit support. A bunch of things were removed. Some ancient ARM boards are the new thing for the final release of this year, 9.2. Some targets have been declared deprecated by their manufacturers, and we also decided to remove them from Qemu. That's Nios 2, which used to be used on some FPGAs and as a soft core, and Chris. The ESP SCSI device used to be a very important device in the 90s. It was completely rewritten from scratch, almost from scratch, by Mark K. Wayland, and the new one is a lot better at following the spec and at following the phases of the SCSI protocol. And finally, for x86 TCG, we have some fixes for 16 and 32-bit protected mode. So if you want to run Windows 95, or 3.1, or 2.0, or 1.0. 1.0 probably doesn't work for other reasons, I don't know. But anyway, if you want to run ancient protected mode, maybe, novel network, there's so many to choose from. We got some new devices, especially in the Virtio space, Virtio Sound and the Virtio-gpu rutabaga, which, if you didn't know, is a vegetable. Also known as turnip or something like that in the British Islands. It's an alternative to Virtual Render. There will be some talks about it in today, and basically the interesting thing is that multiple GPU protocols can be tunneled inside Virtio-gpu, and the main feature that it was created for is Wayland pass-through, and it was merged this year. Also in the build system department, there was an interesting cleanup. If you don't have a host library, now you can choose to disable only some boards. Previously, you could have like this host library is needed to enable a device. For example, the U2F library can be used to enable or disable the USB U2F smart card device. Now the same thing is true for boards. For example, on x86, the only board that needs the device trees is microVM. If you don't have libfdd installed, the build will proceed, but will not include the microVM board. And also, we have a final version of audio dev and audio. It took several years to have something that works, and now you can do like dash audio PA to use Pulse Audio as a default backend for your machine, and there is a model sub option so that you can pick the sound card to use and so on. It's a lot easier to use than the old one. With respect to infrastructure, Qemu.org and Patch have moved from Azure to Oregon State University Open Source Labs. We're still using Azure, however, to run our CI using Kubernetes. That's nice because it can scale out as much as you want, and it can run pretty quickly. And it's not more expensive if you make it faster, which is a nice thing to have. But we also have a new sponsorship from this September, so it's very new, which is DigitalOcean. So we will also look at moving some of the CI to DigitalOcean so that we can avoid putting all of our eggs in one basket. Security. We have more hardening done through the C compiler. For example, the call-used regs can be zeroed, and variables that do not have an initializer will always be initialized to 0. We also move the Coverity runs through the GitLab pipeline, so if it breaks while I'm on vacation, it still runs. And also, big thing that I will talk about later, let's see what was next in 2020 when I last did the Qemu status report. We were talking about moving more stuff to GitLab. Static generation moved there, the primary repository moved there, the issue tracking moved there. We decided that the wiki would stay as MediaWiki because it's a different model than GitLab, and we found a better way to host it as a Podman container, which makes the updates much easier, and therefore we kept it on the Oregon State University infrastructure. And the release processes also stayed the same, so it doesn't use GitLab. And if you wonder why it's 1, 2, 4, that was because that was the idea, was that the release process would have been easier to move than the issue tracking, but that did not happen. So we didn't really get the order or the priority of these changes. But still, we got 3 out of 5, and we have a good reason for the wiki. The release process, maybe, I don't know, something will change, maybe not. We will see. Another thing where we had a little less success was to move more towards API driven way to configure the guests. And one idea was to allow configuration of the virtual machine with QMP by extending preconfig. That didn't really happen. Preconfig mode has been cleaned up a lot, which was nice because, for example, interestingly, as a result of fixing preconfig, you can now use GTK and SDL backends on macOS, which is not entirely intended, but very nice side effect. We were also thinking of having official bindings for QAPI in other languages. So, for example, distributing Python packages or Go packages built from the Qemu sources, and that hasn't happened yet, sorry. However, we were talking about having Rust in Qemu. And at the time, the thing was like, yeah, maybe we can just focus on multi-process Qemu, vhost user servers. But actually, we got this very interesting series from Manos last June. There were lots of discussion, some of them a bit more heated, some of them a little bit more calm. But in general, the attitude, I think we can agree that was positive for everybody. We may disagree on how to get there, but no one seems to be scared of learning Rust, of learning more Rust. There is a concern of having technical debt by rushing too much into code that may not be the best Rust code. We need to also preserve expectations of the distros, the expectation that distros have of a C program, while entering a completely different ecosystem based on crates and very fine-grained dependencies compared to what you have in C. So we have iterated on this. V10 was posted in September, and it seems like it's pretty close to be something that can be merged early. As I wouldn't say as an experiment, but as a starting point to get something that is really usable. Because the important thing is to get it right. Qemu is a mature project and we want to get it right. So one topic was the build system integration, whether to invoke cargo from make or whether to go all in with Meson and invoke Rust C directly. Going with Rust C is not so easy. New Meson is required. You have to write a Meson.build by hand for all the dependent crates. But at the same time, there is work upstream into making Meson understand cargo.log files, which will make this automatic. And we decided in the end that it's a lot cleaner and easier to work with, unless you are the poor guy that has to add a new dependency. We may still have some level of cargo integration still for Clippy, for example. However, we also had to basically fit into what we do for C. We support cross compilation entirely in C code, and we need to do the same for Rust code, and that was a bit easier with the Rust C approach. Also we need to integrate with kconfig, for which there is a solution in Manos's patches, but that may not be the definitive solution. We have something, and again, we will iterate, taking care of not rushing too quickly so that we keep technical debt under control. Another small problem is the minimum supported Rust version. For now, Debian has a relatively old version. There's really just 2 or 3 issues that are interesting 2 or 3 features that are interesting from newer versions. Offset off is probably the worst. We might end up requiring something much newer than 1.63.0 for development, but we will still support building on all the supported Linux distros. This is not 2 of the patches on the list. It's one of the things that we will fix iteratively. Another small issue with cargo is Clippy is adding new warnings on every new release, and we want to have a CI job that builds will nightly Rust, but we don't want it to break every time a new warning is added. So one idea is that we disable all the linked groups, we explicitly list what we want, and when this non-fatal job that has all the groups enabled shows an issue, we can decide whether to enable it or whether it was a one-off that's not a big problem. Final thing, I'm already out of time, so I will go very fast. The immediate goal is to have no undefined behavior, which I'm pretty sure there is something in Manos's patches, but we definitely want to remove that. We want to move towards the goal of having a shared reference for callbacks. And also, the goal is that devices should use safe code or mostly safe code. lower priority, but something that might come for free once we get bindings for error, for QM, for character devices, and so on, is to have also idiomatic Rust code. What does idiomatic Rust code? It means, for example, that instead of having error as a parameter that is passed by reference, you return a result, and then you also don't need anymore to return bool, for example, because you already have the difference. Is this an error? Is this a valid value in the result alternative? We can automatically generate all the extensibility callback and then add some conversion functions. We can have automatic reference counting. One thing that is nice, we can have type safe casting. So if I cast something from device to object, it will only compile if it is actually a subclass. If I try to do a cast from device to PCI device, I need to have error handling. But if I cast from device to object, I don't need to have error handling. So these are nice things that we can do with Rust code, and we will look at it in the future. Who can we learn from? Mesa, who's been an early adopter of Rust with Meson, specifically for the build system. glib and Linux have some different ideas, very different ideas. Probably we'll meet somewhere in the middle about how to interoperate between C and Rust code. Sorry for the typo there. And that's it. Thank you.
Okay, hopefully if you're still here, you're interested in VFIO. Jon Snow's probably the more entertaining talk, just fair warning. So let's get started. I always like to start with a quick introduction of VFIO in case you're not very familiar with it. This is a slide from my 2016 KVM Forum presentation. So if you want an overview of how VFIO works, please go look at that. Real quickly, VFIO is a kernel driver that decomposes a device, all the accesses to a device, into a file descriptor API where user space drivers can then make use of that device. And Qemu in particular is a user space driver that recomposes that file descriptor API back into a virtual device backed by a physical device. So some of the key components of VFIO, we start with containers, groups, and devices, where a group is defined as the minimum set of devices that are isolated from all other devices based on things like Iommufd isolation and isolation between the devices. We add that group into a container. The container represents the Iommufd context. Once we have that group protected by an Iommufd context, we can then access devices. The device presents a file descriptor where the file descriptor is broken into regions, essentially just segments, where each region represents some aspect of the device. For instance, a PCI device, the PCI bars are mapped through regions, the config space mapped through regions. If it's a VGA device, it might have a region mapping that. Not shown here, event FDs are also used for configuring interrupts to devices. And then moving back to the container is how we program DMA to the device. So we map IO virtual address spaces that pin memory in the host system, map it through the Iommufd, and allow the device access. We do that based on a group level, so you can't split IOVAs separate between devices and groups. So what we intend to talk about here today is what we've been doing for the last few years, things that I think are important for the community at large to understand about how VFIO is changing. So we're going to talk about live migration, variant drivers, and Iommufd. So live migration is often seen as one of the gaps for VFIO, where you get the highest device performance, but you tie your VM to a single host or a single device even. So there's been various talks over the past KVM forums about how to implement this. We started out with a version 1 protocol, which was based on a region interface. So we selected one of the regions of the device and had essentially the driver for the device indicate how to interact with that, performing reads and writes to do device save and restore. We didn't place any restrictions on device state transitions, which became a problem, and it was never adopted by any in-kernel drivers. So it was only the out-of-tree NVIDIA kernel that ever used this. So when drivers came along, they wanted to implement an in-kernel driver. We decided this was too complicated and removed it. So for the rest of the presentation, we'll be talking about the version 2, which is the current one that's now upstream, which is more of a streaming protocol. So you get a new file descriptor when you enter, or and invalidated when you remove sessions for saving and restoring devices. So it's much easier to work with. You just read and write from the file descriptor. And we've streamlined the state transition, so we don't allow arbitrary state transitions. We go through defined arcs, which makes things easier for the drivers that need to support this. So in the most basic, minimal state diagram for migration, we enter a device into the running state for compatibility with non-migrating devices. From there, we can go to a stop state and enter either the stop copy state for saving the device or a resuming state for setting the device state. So each transition into or out of these, as I've represented here, a green or blue box, that represents getting a new file descriptor, and when you leave that session, it's invalidated. We're dealing with physical devices, and any transition might generate an error, so everybody has a dotted line to an error state, where to exit that error state, you have to reinitialize the device, put you back in the running state. But also, since we're dealing with real devices, they do peer-to-peer DMA between devices, potentially. We don't have an atomic way to stop all devices at once. So we introduce an optional peer-to-peer support where a device is required to accept incoming DMA, but cannot generate outgoing DMA. So by moving all of the devices into this state, we know that the system is quiesced, and then we can move things to the stop state and continue normally. But also, as we saw in the multi-EFD presentation yesterday, devices have a lot of state. So we can't rely only on a stop copy implementation. So we need pre-copy support, and when we integrate pre-copy and peer-to-peer support, we get multiple states within this saving session and new entry and exit points from the saving session. So typically, you would go from a running state to a pre-copy state to a pre-copy peer-to-peer state to a stop copy state. So the color coding here is meant to indicate red is the pre-copy states, red is the P2P states, yellow is the pre-copy states, and then orange is required when you have that overlap between them. Pre-copy also requires some initial, way for the driver to indicate initial bytes for indicating that the target VM is ready to go and can reduce the latency of starting up the target VM, and also dirty bytes ongoing because the device continues running and continues dirtying state. So that covers the device itself, but the device can do DMA. So the device is potentially perpetually dirtying memory for the VM. And it can do so quite rapidly. With new devices, we have potentially bandwidths of 128 gigabytes per second. If we don't have a way to track the data that a device is writing to, then we have to assume all memory that it has access is dirty, which is obviously untenable. So we introduce some new interfaces for the VFIO device that allow the driver to expose a device-level dirty tracking support, where Qemu can specify an IOV range to track, and it gets a dirty bitmap that is incorporated into the CPU dirty bitmap. So status for migration, the MLX5 and the HI Silicon ACC driver, which is a crypto device, were the two that came along that really proved out this V2 implementation. And that went into the kernel in 5.18. AMD PDS is a network driver that came along in 6.6, and more recently, Intel QAT was added in 6.10. And of course, the NVIDIA out-of-tree driver also supports this new interface. As far as Qemu goes, V2 migration support was added in 8.0, along with dirty tracking support. Pre-copy came about in 8.1, and P2P support, which enables multiple devices for migration, came about in 8.2. So obviously there's a question of where does all this code live? Because we can't continuously expand VFIO PCI for every new device. So the refactoring that's been done here is that we've taken VFIO PCI itself, split it out into a core driver, which becomes a library for what we're calling variant drivers, variations of the VFIO PCI driver. So the VFIO PCI module becomes much slimmer because it uses that core module, and it becomes the de facto variant driver. Then we add a new variant driver for each one of these devices supporting migration. So we have an MLX5 driver, an HI-ACC driver, a PDS driver, and a QAT driver. But migration isn't the only case where we need variant drivers. We also have some interesting other in-kernel drivers that are variant drivers. NVGrace is one of those, where it's a device that when the system boots up, it switches from using the PCI bar directly to using a coherent memory range. And this driver actually presents that coherent memory range as if it were the PCI bar for the device. There's also an interesting device, a Virtio VFIO PCI device, where here we have a physical Sr-iov virtual function that is a virtual NIC, a Virtio NIC. And that device only presents a modern Virtio interface to the guest, but there are requirements for presenting a legacy Virtio device. So this driver works through the PF driver to be able to modify what's exposed to the guest to present that legacy Virtio interface. So as we add new drivers, we have to deal with how does user space select the correct driver for a device. And for that, we leverage what's already done with kernel modules, making use of module aliases, things like the Kmod utilities. So essentially, we take how a driver would typically expose the set of devices that it supports, where it provides an alias, where there might be wildcards in that alias. Here we're showing some examples where VFIO PCI provides full wildcards, while the MLX5 provides a vendor ID and a device ID. Same with the PDS driver. So user space essentially needs to go through the aliases for a device and pick the one that's the best match. And this has already been added to libvirt. So if you have a managed equal yes device using libvirt 10.0, then libvirt will automatically go through and find the most appropriate driver for the device. Also, with the introduction of variant drivers, there's a question of what happens to MDev. MDev is how we started out doing things like vGPU, and it's still used by Intel VGTG, as well as CCW and AP devices on S390X. MDev still exists. It will continue to exist. It seems like it's probably more appropriate when you're dealing with a purely software-defined device, whereas the VFIO variant driver would be more appropriate where you have some sort of Iommufd support for the device. In fact, for a while we had an interface in MDev for specifying an Iommufd backing device for an MDev device. Again, there were no in-kernel users of that, so that was removed. which really pushes things towards using a variant driver when you have that sort of scenario. As we transition from devices from using MDev to variant drivers, there are some hurdles. There are going to be different methods of configuring the device, and we don't have at least the MDev control tool for setting parameters and managing the lifecycle of devices. So that's something as a user you'll need to be aware of. Switching over to Iommufd, Iommufd is proposed to be a new subsystem for the kernel for doing user space IOMMU management. It overlaps a lot of functionality with the IOMMU backends of Vfio, but it intends to support more features such as page faults, error reporting, nested paging, passage support, etc. Vfio and VDPA are the intended initial targets for Iommufd. And given that overlap, we do eventually intend to replace the IOMMU backends of Vfio with Iommufd. So as a result of that, if you want new functionality in type 1, you need to get it into Iommufd first. And then if there is a sufficient need for it in the legacy type 1 backend, we'll consider whether or not to support it there as well. An important distinction with Iommufd is that it provides a device level interface rather than a group level interface. So this is just sort of the paradigm of the interface is groups are hard to deal with and the device interface makes more sense, but the IOMMU group constraints are still there. So Iommufd kind of envisions a world where we have more singleton devices, singleton groups where there's only one device per group. So we'd like to get to that. We're not quite there yet. So under the covers, you still have to deal with groups. So just looking at the flow comparison between the two, in the Vfio API, as I showed earlier, you start with a container and a group, and you set the container for a group, which establishes the IOMMU context for the group, the protection domain essentially, and then you have access to the device. And the Iommufd API, we kind of turn that around. You start with a device and an Iommufd, which is an instance of opening the Iommufd file. That allows you to bind the device to the Iommufd, and therefore you can create IO address spaces, IOASs, within that Iommufd. You can then attach the device to the IOS, which again then makes the device fully accessible. So as you may have figured it out, this requires yet another new interface to Vfio where we actually need to be able to access the device rather than the group. So we create a new character device interface where we can access the device. So you can find this through sysfs. And like VFI, it's essentially a stub device until you map it into an IOMMU context, or at least have a blocking domain around that IOMMU, or for the IOMMU. But once you establish that, then you can get access to the device. You can use the legacy interface and the new interface at the same time, but not across the same group. And this was added in Linux 6.6. So a few notable features of Iommufd. The Vfio container model, each container has a separate IOMMU context, and they don't talk to each other. And that gave us a problem with page pinning between those containers. So if you pin a page in one container, another container doesn't know about it, and we end up with duplicate accounting of that pin paging. Iommufd solves that problem because we have a single Iommufd instance, and you can have multiple IOASs, multiple address spaces within that Iommufd. So Iommufd knows about all pinning within that instance of the Iommufd. Therefore, we won't have to set exceptionally large locked memory limits when we're running VMs with Iommufd. Also, the way we had modeled devices in groups made it difficult for libvirt to pass file descriptors to Qemu for managing Vfio devices. It was always a question of, does VFIO need a new container for a device or not, since we have multiple IOASs within an Iommufd instance, and we can now access the CDEV directly. We should be able to return to a model where libvirt can use SCM rights to pass file descriptors when instantiating a VFIO VM. Iommufd also provides a compatibility mode. So simply by linking the VFIO container file to the Iommufd file, it behaves as if it is a VFIO container. So that should ease transition as we move to Iommufd. And also going back to migration, one of these advanced features that Iommufd intends to provide is dirty page tracking at the IOMMU level. So hopefully we don't have the need for each migration device to support dirty page tracking itself, and we can make use of the Iommufd hardware for that. Status of Iommufd, as I said, we intend this will eventually replace the VFIO IOMMU backends, but we've not officially begun that deprecation process. These compatibility interfaces I mentioned should ease that transition, hopefully making it largely transparent. But at some point we will switch over and hopefully be able to turn off those compatibility interfaces as well. There's still at least one feature gap that we're waiting to be fixed before we can begin that transition, where Iommufd does not yet support peer-to-peer DMA between devices. So you can't actually map the MMIO of a device through the IOMMU using the Iommufd interface. Jason says that's an easy problem. Kernel support was added in 6.2. Qemu support was more recently added in 9.0. So now we have a new Iommufd object for Qemu and a new parameter for the VFIO PCI device where you can specify that Iommufd object to use. I suppose we do allow multiple Iommufds to be created, but it's not really recommended for the reasons I mentioned with locked page accounting at least. libvirt support for this is in progress. Also a note, at Plumbers last week, there was a session on Iommufd, and Jason Gunthorpe provided an overview of where things stand. I won't go over this in detail. You can look at his presentation for more details. But you can see there is quite a bit in progress. And even in the kernel that was just tagged last week, we've added fault delivery to user space. All right, so ongoing work. There's been some discussion about whether VFIO should be taking config space from the device or building it itself. The argument here is that especially if we get to the point of having Virtio devices that are manufactured by different vendors, they might be compatible but have different PCI config layouts. And if the VMM were to build that config space, then we might be able to solve some of the problems that we'll run into otherwise with migration. There's been some proposals about exposing MMIO via DMA buffs, and that might actually be how we support P2P mappings through Iommufd. There was also the talk yesterday about multi-FD migration. So these devices tend to have a lot of state, especially when you get into GPUs and 100+ gigabit NICs. They're essentially their own computer underneath anyway. And then also Ji Wang has just posted a series proposing introducing the NVIDIA vGPU support as an in-kernel open source driver. So that might be our next variant driver entering the kernel. So that's pretty exciting. And then, as I mentioned, there's all sorts of Iommufd potential things to talk about. Nested paging, generic page tables, faults to user space, process address spaces. SVA support is under development as well. And also I'd like to point out Cedric Legautier is effectively, if you've been on the mailing list, you've seen that he is the acting Vfio maintainer for Qemu. So thanks to Cedric for stepping up for that. And I think that's all I have. So any questions? Way in the back?
So, question about Iommufd. Is there a way to subdivide the device, or you have to have the hardware providing a lot of devices?
Subdivide the device as in splitting groups?
Right, like the groups.
Yeah, so you're still under the Iommufd, or you're still under the Iommufd group constraints that you can only have all the devices within the group need to be within the same IOAS. To get around that, we need hardware support to make sure that there's not any isolation gaps between the devices. So you need ACS support in the Iommufd, or sorry, in the downstream ports.
The Virtio Iommufd backend that does the current legacy translation, that was fairly interesting. That means you can add any kind of device emulation behind it. Just expose it as Virtio, which maybe eases live migration a little bit. Has any thought been given to that?
Certainly, variant drivers open the door that you can implement more emulation in the kernel driver. I don't think we want to get into that point of providing arbitrary emulation. So in this particular case, the physical function of the Sr-iov device provides a gateway to enable the legacy support.
How? Just bit fiddling, is that it?
Well, we have to change some of the PCI config space. We have to enable a virtual IO port space. That IO port space access goes through the physical function of the device. So the physical function has to expose capabilities in the Virtio space.
Yeah, makes sense. Thanks.
All right. Great, thanks.
Hi everyone, and thank you for joining us today. I'm Yui Washizu, and this is Akihiko Odaki. And today we will be talking about releasing Sr-iov on virtual machines. Sorry. Okay. なんかずれてますよね。Okay, sorry. First, as an introduction, I will explain the multi-tenant environment. A multi-tenant environment refers to a model where the same system or service is shared by multiple unrelated tenants. When building this environment, there are two main requirements. First, it must be cost-effective. This is a primary motivation for adopting a multi-tenant cloud. In a multi-tenant cloud environment, resources and utilization is maximized by eliminating the need for an infrastructure dedicated to each tenant. Second, it must be a secure environment. And since multiple tenants share the same server in the multi-tenant environment, each tenant should be able to view and configure only their own resources, requiring an independent environment. In such a multi-tenant virtualization environment, Sr-iov as shown in this page is very useful. Single root I/O virtualization, Sr-iov, is a technology that allows a single PCIe device to provide multiple network functions, including physical function PFs and virtual functions VFs. The PF allows the host to configure the VF through the PF. The VF can be exclusively assigned to VM or containers. This technology is beneficial for two main requirements of a multi-tenant environment. By offloading packet switching through the PF, it reduces the virtualization overhead, making it cost-effective. Moreover, it ensures security by assigning network function exclusively. However, in some situations, experience issues when attempting this offload. Next slide. The specific situation refers to container workload. Sr-iov cannot offload packet switching between container within VM. Containers in the VM require their own virtual network, but the VM cannot offload this virtual network to the hardware. Sr-iov can control the VF through the PF, as shown in the left figure. In container workload on the physical machine, admins can control the VF network by accessing PF. However, in the container workload on VM, admins within the VM cannot access the PF and therefore cannot control the VF. And from here, we will present our proposal for this issue, this problem. Okay. To provide an interface that offloads packet switching within VM, we propose emulating Sr-iov with VMM3. By emulating Sr-iov, we can provide an Sr-iov interface, allowing Sr-iov to be used within a VM. In this context, we refer to the PF inside the VM as the virtual PFs, and the VF created through the virtual PF as the virtual VFs. This interface will enable the VM to control hardware through the virtual PF in the future. And there are three advantages of Sr-iov emulation. First, Sr-iov can be treated the same way as in the bare metal system. This allows existing door configuration software such as the Sr-iov CNI plugin to be used as is. Second, since it's not necessary to assign physical PF to each VM, it is scalable. Third, it is Third, it is secure because users are prevented from controlling the entire NIC. Although it is called emulation, it is possible to reduce overhead by using a VDPA and VDPA device as a backend. VDPA is a technology that emulates the control plane while offloading only the data plane. By combining this with the Sr-iov emulation, it is possible to reduce the overhead of container networks. Additionally, since Sr-iov emulation has a pluggable backend, it can be used for other use cases by replacing the backend with a different device. For example, by using a top device as the backend. The Sr-iov capable .inet driver in the guest OS can be used for testing. While Sr-iov emulation provides Sr-iov interface, network functions related to Sr-iov are expressed as device groups in Virtio spec 1.3, version 1.3. Device groups allow the owner device to control its member devices. Several features have already been proposed using device groups, and the provision of interface through Sr-iov emulation also help use these features on VMs. We are considering extending the Virtio specification based on the device groups to achieve packet switching. Currently, the functions to offer packet switching within the VM doesn't exist, and this remains a future work. Although still in the conceptual stage, we are considering processing the TC configuration within the VM via Qemu and offloading it using a bridge that including virtual PF and virtual PF and virtual VF and in the host OVS OpenVSH. From here, I will explain how we combine the Sr-iov emulation with VDPA to reduce overhead and the extent to which performance improved. We verified performance with the following setup and confirmed the performance improvement of over two. Oh, sorry. We from here and we explain. Oh, sorry. Okay, I verified performance with the following and set up and confirmed the performance improvement of about 2 times. This LIVM CNA plugin used was modified slightly to apply to a Virtual CSFS. We verified the performance using Sr-iov VF as the backend into 2 environments with NetPerf as the measurement tool. The baseline environment without offloading in VM used PCI device assignment, while the with offloading environment used a combination of VDPA and SRIov emulation, reducing overhead with Sr-iov. The metrics were throughput and latency, and the measurement section was between container in the VM and external machine. And first, about throughput, the average value of UDP bulk transfer was measured as the result. Both transmission and reception performance improved by 2 times. And latency and the 99 percentile value of UDP round-trip transfer was measured as the result. The latency was reduced by 100 microseconds, showing performance improvement.
It's behaving very odd. Yeah, okay. Now that's I remember the development progress of SR emulation, particularly in Qemu. First, this is the history of SR emulation. So first, because the first RFC patch to introduce SRIov device in 2014, that was for Intel network device, and in 2019 we got better spec for SRIov support. However, the development of SRIov emulation in Qemu kind of stalled for a while, and work resumed in 2022 when we got the first SRIov device NVMe upstreamed. And in 2023, we got the network device IZB upstreamed. And now we are working on Butternet to add SRIov support. From now on, I'm more focused on Butternet. Butternet is, unlike IZB or NVMe, it is parameterized, so it has much more flexible configuration. For example, it can have varying number of virtual functions, and it can also have different backends for different virtual functions. So this provides a lot of flexibility that make parameterized device useful, but it also means we need to somehow configure such various properties. Instead of inventing a new way, I decided to learn from the conventional PCI multifunction. SRIov is somewhat a variant of multifunction, so it will make more sense to follow the previous, current mechanism for multifunction. And for multifunction, it is very simple. We have Qemu devices for each function. We have a Qemu device for each function and add multifunction property to the function 0 and specify address property. So I also decided to have similar interface for SRV. So it also has address properties. Instead of having multi-function property, I added SRV-PF property that pairs physical function and virtual functions. So this allows any kind of virtual function configuration and also physical function configuration. So it looks nice in theory, but it also means the flexibility of configuration is directly exposed to user. So we somehow need to handle this flexibility in the implementation, and it's a bit more complicated. So I'll first explain the challenge with its hot bragging nature. In SRV, virtual functions are enabled at runtime, so it's like hot bragging. But it also has some difference from normal hot bragging. That is, the whole process is controlled by the guest. So in the SRV, the guest configures the resource allocation in the device, and the guest initiates enablement of virtual functions. So it is fully controlled by the guest. So we need to fulfill the expectation of guests. So for example, we need to reserve function numbers and underlying resources such as network backend. And we cannot fail because in physical SRV device, these resources are already included in devices and cannot fail. But that is not the case for hot bragging. And today, SRV emulation literally relies on the hot bragging mechanism. And that's cause mismatch with the model SRV is providing. SRV expects all resources are reserved, but with hot bragging, those resources are not reserved, so that can result in unexpected runtime error. And the hot bragging mechanism is initiated by the physical function automatically. So physical function needs to configure a virtual function and needs to define its own command line interface for this virtual function configuration. If you try to use the conventional command line interface, this command line immediately plugs virtual functions instead of hot bragging. So it is incompatible with the current methodology. So now I'm suggesting to avoid hot bragging for SRV. I have patches for this change. In this change, I decided just to realize the virtual function when the pair of the physical function gets realized. This makes things a lot simpler. It reserves function numbers and resources automatically, and virtual functions will be able to be added with normal device command line. However, just realizing this virtual function will make them visible to the guest, while the guest expects they invisible until SRV until the guest enables virtual functions. So we implemented the disable state for virtual functions. For this purpose, I used the code to power down PCI devices, so it minimizes the additional complexity. And finally, we enable them when the guest requests, and that's perfectly conforms to the model SRV specification provides. The second problem is the validation of SRV device configuration. Unlike conventional multifunction, SR actually imposes as multiple restrictions. So we need to validate those restrictions. Well, usually these restrictions do not matter if you have uniform virtual function configuration and some same address assignment. You can pass those restrictions easily. But still, we have code to check those restrictions are enforced well with the user provided configuration. I also limited the SR device composition to Butternet PCI as precaution, but this can be expanded to other Virtual PCI devices or even other computer-defined PCI devices if wanted. Okay, then I'll summarize this presentation. As background, we talked about virtual network offloading with Sr-iov. By emulating Sr-iov, we can provide configurability to the guest to run run containers on virtual network. There are some proposals to explore the emulated Sr-iov capability for Virtual, and it can even support packet switching if we add necessary interface. And of course, Sr-iov emulation is already there, so we can use it for testing now. And now our benchmark showed big win with offloaded packet switching. That is a kind of simulated environment, so the host configures as packet switching, but still we can show some numbers, and it showed double throughput and latency reduced to third. And we are working on adding a server emulation for Butternet, and I hope this will run in the next version. Yes, so that's all. Any question? Comments?
So I think it's all good. We could maybe, do you think we could maybe make it a bit easier, for users with all these tricky restrictions? Like, like the stride, for example, because the users don't know what the stride is that you put in the capability. So like you're checking them, but against the restrictions that you didn't really provide. Maybe we could come up with. Do you think we could come up with like an easier interface?
I don't have particular plan, but yeah, the address would be the most. The address property is the most tricky one. We need to enforce it has constant stride. Well, perhaps it may be possible to use the existing automatic address assignment mechanism. So this continuous sequential assignment would work for this. So work for most cases. So it will be not that difficult to have some mechanism to automatically assign just to have constant stride 0, 1, 2, 3, and so on. Yeah, but I don't have implementation for that now.
So correct me if I'm wrong. The way I understand this is you use the VFs not for yet another level of virtualization where you pass these in. You use the VFs basically to get multiple network interfaces, right? Multiple data streams across through the host. Have you considered just implementing VLAN tags and making those be part of your data stream?
Well, the current SRV emulation just passed through the network backend, so it does not perform any kind of operation, just pass through. But well, in the future, yeah, certainly we can implement some kind of mechanism into Virtual to handle VLAN or other IP.
What I'm saying is, as an alternative to Sr-iov, so the reason you expose Sr-iov and you want to use Sr-iov is so you get multiple network interfaces in the guest that run on different networks, right? And you do that by basically creating multiple new queues and multiple new devices behind those queues. But you could use the same queues, just use native networking mechanisms like VLANs to steer your actual traffic, which also gives you different interfaces in the guest. So what's the benefit of doing this?
So the virtual functions can be assigned to different virtual machine in the so
Okay, so you're basically, this is for a Kata-like use case where you have another layer of virtualization in your guest.
yeah. Okay. So yeah, it's more like nested situation.
Cool. Then it does make sense. Perfect. Thank you.
Also to emulate how the actual hardware will work, because the vendors now implementing virtual net hardware devices with Sr-iov. So it's kind of emulation of how the actual hardware will work.
I'm super happy with that work. It's great, by the way. Thank you. What I was just wondering about the use case, right? The particular use case for just only Linux in your VM, you can solve differently, probably cheaper and easier and more flexible. This is really, really useful when you do nested VMs.
Yes, no other questions. Thank you.
So we have the patches for Sr-iov refactoring, and also have RSC patches for Virtual Sr-iov emulation. So please check out if you are interested. Yeah, thank you for.
So good morning, everybody. So I think it's time to get started. So my name is Eric Auger. I work at Red Hat in the virtualization team together with Alex and Cedric, for those who attended the VFIO meeting, the VFIO presentation just before. And I'm also the VFIO platform driver sub-maintainer. And I decided to submit this talk because I want to bring up the fact that for some time we have some trouble testing VFIO platform with upstream bits. And so to me, it deserves some discussions, and that's the purpose of this talk. So let's start with some context. So actually, 10 years ago, the topic was quite popular. So we had some presentations at LPC, at KVM Forum. I made my first presentation at KVM Forum 10 years ago about this topic. And at that time, we had some real interest from big ARM players like AMD. So we had a significant upstream effort done. In 2015, we got the VFIO platform driver upstream. It came along with two 10 gigabit Ethernet devices being officially integrated, and I will explain what it means. And at that time, also, we got the Qemu VFIO platform device upstream. So this was the first integration in a VMM. And then, so this is my actual point. So the last integrated device was in 2017 with the Broadcom FlexRM mailbox. And the last functional kernel contribution was in 2018. It was related to some experiments related to the Renesas Aircar Gen 3 platform. And Geert Withoven, so I'm not sure I pronounced the name correctly, so made some contributions related to that, tried to assign some devices like GPIO controllers, and also he contributed the dynamic power management in the VFIO platform driver. But that's basically it. And besides that, so we know that VFIO platform is used. We know that internally because we have some requests to enable the config and so on. But the problem is that it is absolutely not transparent. We have no upstream contributions. And I will try to demonstrate that we should have some upstream contributions. And it is up to the point that now we have a trouble because if you consider the dates above mentioned, so those systems have been e-wasted. So we cannot test anymore with upstream bits. So I was forced recently to resume working on integrating a new device because we had a CV at VFIO subsystem level, and we need to test some stuff also at VFIO platform level. It was related to IRQFD handling, and I was not able to test anymore. So I resume integrating a new device, and I will show examples related to this new integration. So the goal of this talk is to remind that VFIO platform exists. So this is my first goal. I want to re-explain what it is used for and what it is not meant to use for also. I want to explain how to integrate a device because maybe we have not made sufficient effort to explain that. So I want to make sure that everybody understands what is needed. And at the end of this talk, I expect that, I hope that we'll understand the main challenges doing a device integration and try, and I hope you will be able to understand if a device is a good candidate to be integrated in the VFIO platform, or there are too many showstoppers that would guide you against doing this kind of integration. And I hope we will have time to start some discussions on the fate of the VFIO platform in general, because we saw that there is a lack of upstream contributions. And maybe we won't have time during this session, but afterwards. So let's start with the goal of the VFIO platform. So I guess for most of you are already familiar with Vfio PCI. So it is the same principle. So it gives user space control over a physical device, but this time this is a platform device instead of a PCI device. A strong assumption is that there is an underlying physical Iommufd, okay, because it reuses all the concepts that Alex explained before, so Iommufd groups, containers, and so on. So it's really tied to an Iommufd. And generally, you put devices upstream to an Iommufd when they are DMA-capable devices, because otherwise there is no much gain. So that's a really important assumption. So then the user API gives you the ability to have a direct access to the registers of the device, so instead of bars and configs. It allows you to forward interrupts and handle them at user space level. And eventually, so you have the capability to map DMA buffers to user VAs. So it's also tied to the Iommufd. So in terms of use case, so what is first targeted is the capability to write user space drivers instead of kernel native drivers. So it typically targets DPDK like use cases. And besides that, so you may be interested to assign the Vfio, the platform device to a guest. So it's a more advanced use case. And this is what allows the Qemu framework, for instance. In terms of hardware platform, so currently Vfio platform is supported on ARM. And I would say that we mostly target embedded, automotive, and edge platforms. So not servers, because if you have a PCI topology, so you would prefer to assign PCI devices. So this is mostly targeting SoCs which have no PCI access, but sometimes I will share the example of the NVIDIA Jetson Orin system. It has PCI, but it also allows to expose some platform devices. So then I will describe what is needed to support a new device. So I told you currently we have 3 officially supported devices at both kernel and Qemu level. So those are pretty old devices, as you may see. And actually, it's not like Vfio PCI, where you can directly use it out of the shelf, except maybe the new variant drivers that are needed also, that require some adaptation. For Vfio platform, you need to do some adaptation at both kernel level, because you need to support device reset. And if your use case is to expose the device to a guest, you need to add some piece of code in the VMM to expose the device to the guest. So let's first have a look at the device reset problematic. So the trouble is that, so I think it's quite natural to understand that when you assign a device to a guest or a user space driver, you need to be able to reset it. So, for instance, if you assign it to a virtual machine, what may happen is that the virtual machine crashes, and before it has programmed the device to perform some DMA request or to send interrupts. And the problem is when it crashes, so all the Iommufd mappings that were used to translate the DMA request are destroyed, so there is no risk. But when you start again a VM with the same device assigned, the Iommufd mappings are created, and you expose the whole VM RAM to the previous DMA request. So that's the danger, and it will jeopardize the integrity of the new virtual machine. So what you need to know is to be able to stop the DMA transfers that were initiated. You need to disable the interrupts. And in some cases, and we will give more explanation about this need, you need to get and put some dynamic resources that are vital to get the device functional. The problem is that, as opposed to VFIO platform, VFIO PCI, sorry, you have no standard way to reset a platform device. So there is no specification. It can be in registers, it can be reset pins and whatever. So, and VFIO platform driver itself is totally device agnostic. So it has no clue about what kind of device it mediates in terms of control. So we have two solutions to handle device-specific reset. So it depends on the type of booting. So in case you boot with a CPI, so we can use the RST method. So this is currently used with the FlexRM mailbox. So you have an example. And but until now we have mostly covered DT boot. And in that case, what you are using is a custom reset module in the kernel. And this is what I'm going to focus on in the next slides. So you must know that there is a module infrastructure, a kernel reset module infrastructure already in place in the kernel. So what you need to do, if you write a new reset module, it will be automatically loaded on device attached using the device compatibility string that is used for this device. And this reset module is supposed to implement a single reset method, which is called by the main VFIO platform driver on open, close, and on device reset IOCTL. This is how it is done today. So you will find at least 3 examples in this directory in Linux. So in terms of challenges when you write a new reset module kernel, is that you need some knowledge about the device. You need to understand how to reset it. So if you look at the examples available in this directory, you will see that those reset modules are quite simple. Basically, what it does is it picks and pokes some registers which are related to reset. So it enables, it disables interrupts, it disables the DMAs. So it's pretty simple, it's pretty straightforward, I would say. Now it can become more complex, and this is what I'm going to explain. It can require some dynamic resources like clocks or resets, and this is not yet covered by the current implementation. So I told you I was forced to integrate a new device, so I chose that one. So the Tegra 234 multi-gigabit Ethernet controller from the NVIDIA Jetson Orin board. And this device is quite interesting in terms of integration because it pushes somehow the limits we already experienced before. So there is an RFC that is available at kernel on the kernel mailing list. So you can have a look. So what is interesting with this device is that it requires some dynamic resources. So it requires clocks and reset. And as I explained before, so originally we didn't need that because the devices we integrated before were simpler. And in that case, what I needed to add is 2 new callbacks besides the actual reset function. One callback which is called on init, and the other one which is called on release. And the job of the implementation of those callbacks for the Tegra 234 MGB reset module is that they are going to get and prepare the clocks and get the resets. So you make sure that all the dynamic resources are there before giving access to the VM. So this is new, and so I hope this will get some traction on the Linux kernel list. Kernel mailing list. And so logically, it should allow the integration of new and more complex devices that require dynamic resources. So we talked about the integration, the adaptation needed at kernel level. So if your target is just to write a user space driver, so it's sufficient for you. But if you want to expose your device to a guest, so you need something more. So this time you need to do some adaptation at the VMM level, because the problematic is that for platform devices, you have no PCI-like bus enumeration, so it's not enough to expose the platform device to the guest, so the platform device object. You need to write a description what this device looks like in terms of SCPI or device tree. So in that case, I will mostly focus on device tree aspects, and I will give you some examples. So there is currently a Qemu integration for Vfio platform. So the principle actually is that when you pass this option to the Qemu command line, targeting the assignment of this Ethernet controller, so behind the hood, Qemu uses what is called the dynamic sysbus instantiation. So it uses a so-called platform bus, and then it creates the Vfio platform device and plugs this Vfio platform device to the platform bus. So there are helpers already in place that find the right MMIO slots, the interrupt slots, and it connects all that stuff transparently to the interrupt controller, for instance, and so on. So you do not need to care about this Qemu object topology. This is done for you. But what is needed is to take care of the device tree generation, because this is purely device specific. And this code can be found in this file. And you will have at least 3 examples today, so for the 3 integrated devices. And there is a new proposal for the Tera 234 MGBE also. So the principle is quite simple. So you have a binding structure that associates for each compatibility string a device node creation function. And so Qemu looks at the device you want to attach, is able to fetch the capability string, and knows that it needs to call this function to create the device tree representation of this device. So here is the first device we integrated. You can see that the device tree node is really simple, just 4 properties. So the register properties that tells which registers are exposed, the interrupts, compatibility string, and the DMA coherency property. So what you need to do, so this is the device tree node on the host. So you need to create basically the same stuff on the guest. Okay, but we have, so in the sysbus.dt file, you have helpers that will help you to locate the address the device was put in on the guest side. You will be able to retrieve the size of the regions, and you will be able to retrieve also the SPI interrupt the device is plugged onto on the guest side. So it's fairly easy to build that device tree node on the guest. So I would say this one was really Vfio platform friendly, very simple device tree node. So it was a fairly easy job. So now let's have a look at the second device we integrated. So you will find exactly the same kind of properties we described before, but this time, so we have plenty of device-specific properties we need to generate. So for those, so what was done actually, we are fetching the values of those properties on our side. We are copying them and pasting them on the guest device tree node. So it's quite easy as well. But you need to understand, when you do that kind of job, you need to understand the properties. So there is some knowledge needed. So it's not like plugging a Vfio PCI device. So you need to look at the binding descriptions and so on. So this is the kind of job you need to do. So the additional challenge we had is to handle the clocks property, because here you can see some reference to external clock nodes. And the problem is that you will need also to generate those nodes on the guest side. So it becomes more complicated because you don't have a single node anymore. You need to generate some providers for some resources. So it's obviously more complicated. But it was fairly simple in that case because we were lucky enough that those clocks were stable. So fixed values, fixed clock property, meaning that the clock frequency is stable, and we can just copy the nodes that you can find on the host and copy them on the guest. So hopefully this was quite easy. So now let's have a look at the Tegra 234 MGBE. So this is the next level. It gets much more complicated because on top of the previous properties, so you will find also clocks and so all the stuff we described before, but now you have resets. You have interconnects, you have power domains, you have a phi handle, P handle, and you have a M-dio sub-device. So it starts to be much more complicated. So luckily, so this is an experiment today because so it's an RFC on the Qemu side. I was able to get rid of some of them which are not requested from a binding point of view. If you look at the documentation in Linux, for instance, interconnects, this is not a mandatory property. So I got rid of that. I got rid of power domain, but yeah, I was cheating on that one because so theoretically this is mandated. But so in practice, the guest is happy with that, at least for the moment. For the phi handle, I got rid of it, but it is requested also at the moment. The M-dio stuff is not requested, so I got rid of it. However, the reset is not optional. So if you don't expose any reset on the guest side, it won't probe. So the device won't probe. So you start crying because in that case, what you need to do is to generate a reset controller DT node on guest side. And if you look at the P handles that are used in this device tree node, so it refers to what is called the BPMP. This is a specific IP on the Tegra hardware that manages all the resources like reset, clocks, power, and many more. So, and the problem is that you cannot expose that to the guest because it drags other dependencies. For instance, you need a mailbox, and without, so I try to expose this mailbox to the guest, but it requires some emulation because it tries to read some registers when probing, and if you don't have this register, it fails. So the only solution I found is to use a iSilicon reset controller, which has another dependencies on the syscon device, but this one probes gets probed properly, so it's not a problem. But so it's somehow the same problem as clocks. So you expose some stubs on the guest side, and so you see the limit of this technique, because if the guest tries to use those resources, so it may have some consequences. So eventually, here is a representation of associated to this node that I was obliged to expose to the guest. So as a conclusion, so there are definitively some showstoppers when integrating a new device. So if you try to assign a GPIO controller or something like that, just to blink LEDs, there is no Iommufd, so it will be rejected, and we are not supportive of such use cases. There is another issue if you have dependencies to DMA controllers, in which case the DMA controllers have a relationship with the Iommufd, and it's more difficult it won't be possible to assign the device. You would be obliged to assign the DMA controller itself as a whole. So we have seen that I expose some DT node stubs to the guest, and sometimes it won't work because you need some emulation. So there are some issues if you have shared resources also. If you share a reset with another device which is used by the host, it's a problem. So those are showstoppers. Now, what can be troublesome is dynamic resource management, but we should be mostly okay with the extensions in the reset module. And it's hacky, I would say, to generate stubs on the guest side. So this is something problematic. And Sorry. And so also you need to be aware that the native driver maintainers should be in the loop because it requires knowledge about the device. So you need to have their hack when you do such kind of exercise. So they must be in the loop. And it's a problem also in terms of maintenance. Okay, so what would be really helpful is to have virtual functions. Because if you get some virtual functions, even on platform devices, it will reduce the dependencies on external resources, on external resource providers, because the physical function will handle those and will simplify a lot the description you need to make on the guest side. So this is really, I would say, the future if we really want to use simply VFIO platform to assign to a guest. So now I come to the actual discussion. How many minutes do I have? 5 minutes, so it won't be sufficient. So besides all the difficulties we have seen before, I don't think this is the actual problem because we are all engineers, and so I think we can fix solutions, find solutions. But the actual question is there a real market segment for VFIO platform assignment? So there are some customers, but it's unclear what they want to do. And also, we would like to see some concrete contributions upstream, because so the reset drivers are mandated. Maybe the rest we can ignore what they do, but the reset modules are mandated. And if we don't have that, to be honest, there is a high risk of driver deprecation because we cannot test it anymore. So of course I can maintain an out of tree integration, but is it my job? I don't know. So it's questionable. And the last word is that so I'm totally willing to help for new device integration. If there is a real market traction for some device to be integrated, I will be glad to help. So Alex.
Was that obvious? Awesome, great. First off, I'm happy to kill it. I was the biggest proponent of this whole VFIO platform 10 years ago. It didn't take off. It was an experiment, fair enough. A couple of comments. You're cheating a lot, right? Especially when it comes to clocks. Not all devices are happy with fixed clocks or happy with just a simple reset type of logic. Yeah. So if you would try to go and do the same thing with, for example, an MMC, like an SD controller, all hell would break loose. Like you wouldn't be able to talk to any device.
And this is what you told in 2013 in your LPC presentation. So I'm not surprised about that. Effectively, some drivers need to actually set the clock frequency, you are dead, or you need emulation. And I mentioned the interconnect property also. It's set to constrain or to ask for a given bandwidth on the subsystem. So this is the same kind of... so at least, so that's true. I'm cheating in many places. Maybe this is acceptable for some use cases. I don't know.
No, the whole point of this exercise of merging the Hacky code and getting that going was to tap the foot into the water and see whether there is actual desire to go and improve going forward. We haven't seen any. Yeah. Like all the devices that ever were used with this are pretty much dead at this point.
Yeah, totally.
There is just simply nobody that cares. And if they do care, then we can remove this and then have them resubmitted upstream with a sensible modern interface and architecture. So what we would need to do is we would need to basically adopt Alex's variant mechanism, where you don't have reset drivers, you really have specific VFIO platform X drivers, right? Then the next thing you would need to do is these drivers would need to implement generic, more or less generic interfaces into user space that give you access to what effectively the kernel APIs for setting clocks, performing a reset, all of these APIs, but safeguard them, right? Make sure they're actually safe. And then we would need to implement PV, clock setting, PV, power domains, PV, any of these things, so you don't have to expose a high silicon device into a random board, right? So all of these would then become PV drivers, and that's a lot of work.
Yeah. So that's actually the question. So is it a real market traction to do all that stuff? So if people want to keep the functionality, they need to contribute also to that.
The easiest way to find out is by removing the code And if somebody shouts, you tell them, happy for you to be the new maintainer. Go and, like, we have a list of things you need to do. Please go and resubmit with this new.
Yeah, but actually, this is what we plan somehow to do. So if we are not aware of any...
Kill it now.
Okay, so it's an interesting discussion and outcome.
Just kill it.
Thank you. Any other question?
Fortunately, we are out of the time.
Yeah,
so
sorry.
Thank you.
Okay, thank you very much.
Thank you so much. Thank you so much. So hi everyone. So yeah, we are going to talk about CXL stuff because yeah, I think many of you also saw me like hanging around in LPC to talk with CXL maintainer folks, and also here I talk with Alex and Cedric for basically talking about the ideas and the patches has been sent in the mailing list. So but now we're going to jump into the slides, more stuff about this. Yeah. So before we talk about the VFO CXL stuff, so I would like to give a bit, brief introduction about the CXL. Yeah, because I'm not sure, how many of you have been working on that. So for CXL device, so mostly like, it's built on top of the PCIe actually infrastructure. So there has been like 3 different kind of like protocols here, introduced mostly for achieve the purpose, for device coherencies, for memory expander, and also for accelerator, for different usage case here. So they have 3 types. So type 1 is the device which only have this so-called CXL.io and CXL.cache. CXL.io mostly is equivalent to the PCIe, so it actually provides you interfaces with non-coherence load and store. Yeah, and CXL.cache is mostly a protocol to maintain the cache coherency between the device memory and the host. So it's mostly a protocol. If you read the spec, it's mostly a protocol to maintain the MESI states actually between the device and the host. And also be aware that like the device can do self-flush right now. Yeah. And CXL.mam. So CXL.mam is actually a protocol to provide the capabilities for the host actually to directly access the device memory. So by combining these 3 different protocols, actually, then it comes to the the types. So for these pictures from the spec, so type 3 devices mostly is the memory expander. So it's mostly like after you set up the device, so the device memory will be online, it will be part of your system memory. So the ultimate goal of memory of these kind of Type 3 devices, like they can do memory pooling. Means like you can have a super huge, kind of PCB board, a lot of memory DRAMs there, and then you can feel free to assign it to this node and that node. That's their ultimate goal. And Type 2 devices are mostly like accelerators. It's more like, the common usage of programming the accelerators with additional support from the CXL. Yeah, and also like recently we also saw like there's accelerator also doesn't have this coherence cache, but they only have 6.mem and 6.io. So the patches under review is AMD's SFC Ethernet. So I also review the RFC patches like V2, and now it's going to V3. So the patch has been much more solid than before. So let's see how it goes. And the layering. So for CXL layering, mostly like, CXL.io reuse as much as, what PCIe provide, transaction layers, link layers with some small enhancement there. So basically you can see configuration space, you have MSI, MMSI, all these kind of things. And down there's actually a fabric which can actually recognize two different flows coming from the top layer, so it can navigate the flow to the correct logic there. So basically you can see like CXL.io reuse everything mostly from the PCI, and CXL.cache and MEM, they have their own encodings because their purpose is different. Yeah. So that's actually the layering. Programming interfaces, I think this is the most things I think our software folks cares about. Before you're reading the specs, this will help a lot to help you to understand all these things. So basically, the programming interface of CXL device contains two parts. One part is located in the PCI configuration space. Yeah, the other part located in the PCI MMO register. Yeah. So mostly like in the configuration space, they add a lot of DVSEX, the vendor actually capabilities there. So you can see like there's a lot of stuff there. Sorry. So one of the most important part. So one of the most important parts is called this register locator. Register locator actually give you the pointers to which part of and what kind of a register group and where they are located in the MMO register. So mostly it will give you an address like, to index to a bar. And then like, in this bar where, and with the offset, like where is this register group actually in the bar. So in these slides, actually, I call it CXL MMO bar. Yeah, but basically, it has two parts. One part is in the configuration space. The other part goes to the MMO. For the registers, there's actually like four parts, actually. One part, the common one, actually area of the type CXL device implemented is called component registers. So inside the component register, there's control of CXL.mem and RAS, and some control of the ARB MUX. Yeah. And then second one is called bar virtualization ACL. So mostly it's for our virtualization folks, I would just say. And then like the device register used to call CXL memory device register is mostly for the Type 3 device, which provide an actually mailbox there. You can actually talk to the fabric inside the device to repartition the device, and also doing a multiple control on that. But most of the Type 2 device doesn't use that. Yeah. More about CXL. So spec is always helpful, and also mailing list there. And also like CXL folks, they have a very helpful Discord channel. A lot of things have been discussed there. Quite helpful, and people are quite welcoming, not afraid of asking even basic questions, and there will be people answer that. And also like we have this open source collaboration monthly meeting there. So if you really need to discuss something like in the meeting, just feel free to join and join the Discord. Ask people to forward you, then you're on board. Yeah. Oh, why Vfio device for Type 2 device? So sorry, why Vfio? Because there has been a discussion about this in the CXL Discord group. So because for type 3 devices, they totally, the CXL folk, they are totally not using VFIO at all because its nature is more like a memory. So they are going to Virtio mem. And also there's a lot of features I think they are going to add it to Virtio mem, mostly, about taggings, how to do the partition and all these kind of things, super complicated, I would just say. Yeah, for the programming model of the CXL Type 2 device and how you are going to use it is quite similar with, accelerators and, operating or normal like PCI device, So that's the reason like VFIO actually is chosen to actually host this. And also like virtualization models are very compatible with each other. They have this common I/O virtualization approach, virtual function, pass-through, PF pass-through, all these kind of things actually. So we pass through the whole device, not only a portion of the memory actually. So, and then it's like there's a lot of stuff in VFIO actually, we can already leverage because, this CXL Type 2 device, they have all these interrupt. We in VFIO PCI Core, we already have interrupt deliver, all these kind of things there, right? And also configuration emulation and all this framework where we can leverage. So yeah. And then, so this come to the architecture pictures. So as you can see, like the legend here, the green part is something we're going to add, and but it doesn't fit the RFC patch there yet, sorry, yeah. And then the yellow part is what has been there, but we are going to change, sorry, not we are going to change. And, this actually part is actually something we're going to change, yeah. So basically the idea is like virtualization policies is like for configuration registers. So we are going to, emulate them, which has already been like part of them in VFL PCI Core, yeah. And MMO registers, so we are going to do the immediate pass-through because there are many registers in the, let's say, for example, HDM decoders where you can specify the CXL region is actually in the bar register region, MMO register space. And then like they are going to write the GPA there, right? So, I mean, in the very common virtualization practice, so you have to do the GPA to HPA translation, all these things. So yeah, that's the reason why it's immediate pass-through, yeah. So the thing is like we would like to stick to the current, model of the VFIO PCI Core, trying to have a core and a variant driver. So the purpose of the core is trying to, put a lot of, as many as the common things there, and to simplify the implementation of the variant driver. And meanwhile, because the initialization of the CXL device is quite complicated, you see a lot of register there and all this kind of thing. So we are going to leverage the function from the kernel CXL core. But of course, the patches is currently under review. So we are mostly going to expose the function required by the CXL core from, from the latest kernel. CXL core, and the others is like we're going to introduce CXL aware to VFIO PCI Core to leverage, all these PCI stuff. Actually, what a CXL device have, yeah. And after all this is done, so we actually going to, have because we know currently QEMU have a PCI stop there, right? So VFIO PCI stop there. So we need to have a similar thing, either a new one or stick to the current one, yeah. And then like, QEMU, the current code will, put this CXL device into the, the CXL topology in QEMU, which is in the mainland already. Yeah. So, yeah, as you see, like, the core layer is actually the helpers for the variant driver, to eat the burden of variant driver. So, and the core functions is provided mostly the CXL reset. So as you know, like CXL reset, CXL has its own reset. It's so not as the same as the PCI function level reset. So some device supported, some doesn't. If you go the function level reset for the CXL, so it's only reset the CXL.io. So that has been mentioned in the spec, yeah. So CXL reset needs its own reset there. And maybe some vendors, they will have their specified, sequence or something like that. So they can feel free to override this. And and then interrupt management delivery, we have already have, all these routines, how to deliver interrupt, through the event FD, all these things. So all these things has been there. So the core should leverage the VFL PCI stuff there. CXL region management. So mostly like, we need to actually fill the information need by the kernel CXL core, and then let the CXL core to create the CXL region for us, and then expose this region to the user space, and we have this region ops, all this thing. Configuration space has been talked about that, so we are going to let the VFL PCI core to manage it because it's totally emulate. But still, like, because of this core and the Varan driver infrastructure, so the Varan driver, vendor driver, will always have the choice to, I do everything by myself, or I only do something I'm interested, and then the rest thing, if I'm not interested, I just throw it to the core. Please go and do for it, like that. So the idea is still the same. And CXL MMO register, so mostly trying to reuse the PCI core to manage the bar MMO register, because currently like in the code we have these prop MMAPs to check if a bar actually can be transparently passed through, right? Not able to, not necessary to be trapped and emulated, through this read and write, right? So we would like to stick to that for the bars, or not for CXL. So for CXL bars, we are going to emulate some of the register. Yeah, emulate some of the registers. Yeah. So, and Varan driver. So the Varan driver is mostly responsible for first provide the device info, because, for example, your DPA space, RAM space, all these things is not actually regulated by the CXL spec. So I mean, like you Varan driver, knows all this information either from your vendor space register or something like that. So for that part, the kernel CXL core need them to create the CXL region. And after you create the region, you also need to tell the user space what kind of region you created, like that. So yeah, basically currently the RFC patches is very simple, but I would like to see more use case from the other hardware vendors. I will introduce the hardware vendors later and the people who work on that. Yeah, and by the way, we also have the ultimate choice, like we can do this or by the vendor specific driver. So VFL Varan driver there. We have the choice for that all the time. Yeah, so. Required VFL core changes, some of them has been mentioned, and yeah, because CXL device doesn't have this old legacy INTX interrupt, so mostly use MSI and MSIX or these modern things. So yeah, so we just need to tell, okay, we don't use that anymore in the PCI core if it's the PCI, if it's CXL device there. Yeah, awareness there. Yeah, currently in the RFC code, it just has a CXL, it's a bit there. So if it's set, so the VFL PCI core knows, okay, this is going to be operating on the CXL device. And yeah, and bar memory propping. So yeah, that has been talked already. And device reset. So mostly like we would like the CXL core to handle it, not let the VFL PCI to touch it, VFL PCI core to touch it. Yeah. And also like, VFL PCI core will see, oh, this is a CXL bar, so we won't touch it like that. So when doing the MM probing there, so Qemu changes. So yeah, so currently like, we have to introduce CXL device awareness there. And also like we need the DOE support, because in the spec, you can see when describing the memory of the type 3 device, there's an option like, okay, I don't describe in this register, I describe it from the CDEC, from the PCI DOE box. So that for that part, we have to, find a way to feed it into the guest, so it knows the nature of the memory there. Yeah, but I mean, this might be very straightforward because the DOE support in the PCI subsystem has already been there. So yeah. And the CXL device support setup. So mostly like a new cap is introduced for this CXL device. So mostly like, it will tell whatever the QEMU need, so that QEMU doesn't need to actually do all this probing, all these things again. So it can directly get the stuff from the, either Varan driver, like that. So mostly currently stuff there is like the HDM register decoder and HDM count and DPA size. So yeah, I think this is heavily dependent on the usage case, I would just say, because currently there's only one requirement is like we have to trap the HDM. And then like you can see the programming interfaces pages, there are a lot of stuff you have to jump from here, and read and write all these things. And VFL6 core has already have it, so you just feed Qemu, go and take it like that. And then virtual HDM decoder commit. So when the guest want to create the CXL region, so it will program the HDM decoder register there, which means like, it will trying to, put the GPA there in the, in the base, and then the size in the HDM size register, and then write the commit bit. And then it goes to the QEMU. QEMU will know, oh, this is going to be a HDM decoder commitment. So I'm trying to poke, the memory slot thing and to change the GPA and HPA mappings. Yeah, so yeah, basically it's a little bit similar like the bar address change in the QEMU. Yeah, so it's not something new actually. So this is a summary about the CXL device support in the upstream. So currently, in-tree Type 3 device has been there because it has been there for quite a long time. And Dan Williams, actually, the CXL maintainer, actually has Type 2 device support patches reviewed, but not in tree because they don't have the Type 2 device right now. Yeah, and what it's doing is like it has already done a lot of very fundamental work. And then AMD, they have, just what we talked about, like they have an Ethernet device, which have the CXL support there. So they take over Dan's patches and post, the support of the Type 2 device supporting the core, and also the support in their device current driver, because the driver has been the main lane. They want to enable the CXL support in the driver. Yeah. So patch title series has been like that. So I left some comments there, and also like feel free to jump in if you want to ask something, or in the Discord. He's also in the Discord group as well. So if you want a quick answer, just jump there and ask. QEMU support. So QEMU has already been supported the CXL 2.0 topology, means like it can build a virtual CXL topology according to the QEMU command line, a little bit like VFL PCI the virtual PCI topology in the QEMU that has been done there. And also it can emulate a Type 3 device. And also there's a Qemu patches to, emulate the Type 2 devices, yeah, which is also done by another CXL maintainers. Yeah, so, but it's not going to the upstream, so they just trying to imagine what the Type 2 device need, what it need. And now there are like 2 or 3 Type 2 devices coming up. Just one is the emulated one, because CXL folks love QEMU, so it's something like they can play around without any, and also NVIDIA and also AMD. So yeah. CXL core kernel changes, currently there are not so much. Actually, I have already been talking with Jonathan and Ari and also Dan about the changes we need, and the feedback is quite positive. They said, well, it's fine as long as you need all the stuff. I mean, you're the only 2 drivers there. If you really need it, you just let us know, it's fine, just put in the correct place. So currently what we need is the HDM decoder count, HDM region count, and component register. Where is the component register? Because HDM decoder is sitting inside the component register, this CXL.cache and the mem. So, and also like the offset of the HDM decoder register block inside that area. So because that has been probing by the VFL PCI already, VFL CXL core already. And changes for the CXL Type 2 device we need there, and the patches on the review. And also in the latest RFC, actually on Alejandro actually addressed the comments from the CXL folks and me. So they reviewed the assumption of a register group, like Type 2 device have a memory device register group. They removed the assumption there, but currently my repo is still there because my tree is based on his RFC. So once his V3 is reviewed, so I will rebase to that tree. So this will be there already. Patch set. So I actually post the patch set in the mailing list. So the goal of the patch set is actually to provide a code base for people to discuss, because it's I think it's quite efficient for people to have a code to discuss, so you can see like what the code would eventually look like. I think it's better than we just discuss in our mind and we really don't know what is going to be landing on the code, because some of them might be we might sometimes be too optimistic, or sometimes we might think it's going that much worse. But actually, with the code, I think it's much easier for people to see and to discuss. And also beside that, so I provide an environment for developer can test with. Means like, you can try the code and how it looks like. So, and yeah, so the status currently is like you can test the RFC patches with this nested virtualization. So I don't know, I know many people doesn't like nested virtualization, but it's fine. So this is just for test. And with virtual device pass-through. So which means like I actually, refine ARIAS patches. So the QEMU host actually emulates a generic type 2 device there. And then, all these VFIO6 cores and the changes, they are going to be loaded in the L1. And then the L1 QEMU will have this PCI stuff support for the 6L. And then with all this stuff, you can actually start another L2 guest. And then in the L2 guest, I actually wrote a dummy, 6L driver, which will attach to this common 6L type 2 device provided by QEMU. So you can actually prototyping, all your driving load sequence and, the ABIs and, the infrastructure things. So yeah, so mostly that's the purpose. And Alejandro's patch is still under review, the patch 3. So after his review is done, so I will rebase all the stuff there. So yeah, but I mean, yeah. So the last part is the call for comments. Actually, I have been hanging around with a lot of guys, about this. In the LPC, actually, I went through the patches with Aria and also Jonathan, the maintainers, and also showing them the demo and, asking for the feedback. So trying to grab people on board. So they are on board. And now with this presentation, we put virtualization people on board as well. And also, I reviewed Alejandro's patches and also had many talks with him about, the next version of the patches. So device vendor is also on board as well. I think we get quite a lot of necessary people to start the discussions based on, it's not about the patches, it's about what you want and what you want it looks like in the future. With the patches, I think it's much helpful. You move on the discussions. So right now we get those folks on board, and also I was looking for more device vendors, get on board and ask what you want from a virtualization perspective, or the native case. I would just say, because I only know what NVIDIA need and what AMD folks need. Yeah. So, but yeah. And then the comments is the kernel core changes actually has been, we have been go through that with them. And then PCI core changes and the 6L core changes, mostly there has been some discussions about, how to maintain the 6L changes, because not everyone's familiar with 6L changes. And there's also a lot of good comments from Alex. So yes. So, I mean, just feel free to put more of your concerns oh, I want to modify PCI core, but I don't want to, I don't want to mess with 6L core, so what you can provide. I mean, that would be very good questions, I would just say. Just feel free to jump into the mailing list. And UEBI for QEMU. I think QEMU actually have the same, opens from the maintenance and also, how to separate people with different background, actually. So yeah, feel free to jump in. And the device vendors requirement, just talked about that. So who should be included, and also last is, I think the outcome of all this discussion at the end would be what would be included for the V1, which everyone on board is happy. Yeah. So, and yeah, so this is the checklist, what is in the RFC patches, and also there's a demo video. The demo video is mostly also for other people who doesn't have so much virtualization background, to make sure they don't encounter a lot of problem all the time, so they can get exactly the output I get. So yeah, the patch that have been there, demo, I think I still have some minutes, so I can finish the demo. And if you get more questions, I mean, just feel free to come to me, or just join the 6L Discord group, or you throw the comments in the mailing list, I would just say. Yeah. So this is you are going to start your this is in the host, actually. So you can see my command line here. Actually, I would like to show you my command line so you can just directly use it. And then you start your L1 guest. So yeah, it takes some time, and yeah, 44. I think I have some minutes to finish it, right? So it's 44 yet. Okay, yeah. So yeah, and then I can accelerate a bit because this is like something like jumping all the time. Ah, oh what? Okay, so oh. So I think I have to stop my presentation first. Oh, I'm sorry. Yeah, but thanks so much for letting me know. I just didn't notice that. Okay, if I stop it, please stop. No. Okay, I stopped it. So I think basically we can see it now. So yeah, I will quickly jump into the important points. So this is the command line here, actually. So what you are going to do is use it to start your L1, and then L1 started, and then here's like you're going to use the command line I provide you. First, like you're going to reload, very typical things like load the PCI core and then CXO core, all these things. Sorry, 1 minute more. I will finish this very soon as possible. So. And then you load it, and then there's kernel command line. You need to add it. So this one actually. So, and then in the video you can also see the command line I used to start the L2. So with this command line here, so yeah, you can start your L2, and then in the end of it, so you start your L2, and from the dmessage you're going to see, the dummy driver. I applied, I offered actually get loaded, CXO origin get created. So, and all the code you need was actually in the repo mentioned in the cover letter. So feel free to hack and provide feedbacks and join the discussion. I'll just say it will be fun. Yeah. Okay, thank you so much. Thank you so much. Yeah.
Okay, let's begin. Hello, everyone. My name is He Xin, software engineer in ByteDance. Today, my colleague Hong Hao and I will give you a topic about the challenges of building AI infra on virtualization. Here's today's agenda. The first part covers the problem of building AI infra on virtualization. And then we will introduce our design and implement to resolve the problem. And the third part involves the future work. Okay, let's begin the first part. The PCIe communication efficiency between GPUs or GPU and NICs is crucial for large-scale model training and inference. But in virtualization scenarios, there will be a serious performance degradation due to the enablement of Iommufd. And the other problem is that due to the frequent PIO and RDPMC operations, there will be a high number of VM exits. The next part, I will introduce our design to improve the PCIe communication efficiency that we call this solution direct P2P. This figure shows the read or write TLP transmission path when disable Iommufd on host. Now, because the TLP carries the HPA and the NIC can read or write GPU memory directly. When we enable Iommufd and and the GPU and the NIC are both passed through into one VM. Now the TLP will carry the LV, and it can't be routed by switch directly. The switch will redirect the TLP that carries the LV to root port, and the Iommufd will translate the LVA to HPA. After this, the switch can route this TLP directly. So that we can see now, due to the enablement of Iommufd, the transmission path of the TLP has been changed. In addition, that the switch relies on the access control service to redirect the read or write TLP and the read compilation TLP to the root port. Now I will introduce the main control bits of ACS, such as request redirect and compilation redirect. If these bits are set, all the TLP, such as the read or write and the read compilation, will be redirected to the root port by the switch, and the direct translated bit will be introduced later. So due to the transmission path has been changed, that there will be a serious performance degradation, and the write and read speed has been reduced from 196 to 121 and 170 gigabits per second. So to avoid the performance degradation, that the NIC in VM can support ATS capability, like this process. Our purpose is that the transmission path of the TLP for the device without ATS in VM is the same as the transmission path in host disable Iommufd. So if the switch can route the TLP directly, the TLP must contain the HPA, and if the NIC with ATS supported has a local cache, that we call it ATC. So let's look at the process. Initially, the ATC is empty, and if the NIC want to read or write some data to GPU memory, first it will send a TLP request. That we call this request address translation request, and this request will also be redirected by the switch to the root port. And the Iommufd will receive this request and translate this request, will translate the LVA to HPA. So after translated, it will respond a TLP to the NIC. The NIC will receive this response and store the LVA to HPA mapping into its local cache. Now, with the local cache, the NIC can send a TLP that carries the HPA. A special thing for this TLP is that its AT field is 10. So now we can see that we can get a TLP that carries the HPA and its AT field is 10. But for the switch, how does can identify this TLP should be redirected to the Iommufd, or this TLP carry the address can be routed directly. So now we have mentioned about the direct translated bit of the ACS will be used. If this bit says, the switch will check the AT field. The switch will check the AT field of the TLP, and to determine whether the TLP contains the HPA. If the direct translated bit is set and the AT field of the TLP is 10, now the switch will believe that the TLP carries the HPA and will route this TLP directly, regardless of other ACS control bits such as redirect request. So through the above method that we can see, for the device with ATS supported in VM, the transmission path is the same as the host disable Iommufd, and the performance is also the same. Okay, like this. So now we have introduced the transmission path of the transmission path of the TLP when disable LMU in host, when enable LMU in VM without ATS and with ATS. So our problem is that for the device without ATS in VM, is it possible to ensure that the transmission path of the TLP is the same as the host disable LMU and with ATS supported in VM? Like this. We want to ensure the transmission path is like this. So there will be two questions. The question one is that how to get HPA without LMU, because now the switch, because we want the switch will not redirect this TLP to the LMU, so we must get HPA without LMU. And the other question is that how to avoid the ACS redirection, such as read or write and read completion. For question one, normally we need LMU to translate the LVA to HPA like this. But there may be a corner case that the translated address HPA is equal to the address LVA like this. So maybe now the switch can route this TLP based on the LVA address directly, because now the LVA is equal to HPA. For question two is that we just need to disable all ACS control bits to make sure that the TLP will not be redirected to the root port. Let's look at the detailed design. Okay. Our purpose is that for the device without ATS in VM is the same as the host disable LMU and with ATS supported in VM. As mentioned above, when the LVA is equal to the GPA, the switch can route this TLP based on the LVA address directly. So that we can get this transmission path. And another thing we need to do is that to disable all the ACS control bits. So now the switch will not redirect the read or write TLP and read compilation TLP. It will route all the TLP based on the address of TLP directly, regardless whether it's HPA or LVA. So that we can see that about method that to ensure we will get this transmission path, that we modify the VM BIOS to ensure that the GPU bar address space in VM is the same as the address in host. And another thing by this, now the for example, when the NIC want to read or write GPU memory, and now they are in the same VM, the NIC now receives some data from other hosts and want to write this data to the GPU memory. Now the destination of the write TLP is the GPU bar address in VM, because now we have modified the BIOS to ensure that the GPU bar address GPA in VM and HPA in host are equal. So now the switch can route this TLP, TLP based on its HPA address, and the TLP will correct. Here's through the direct P2P solution that we can see that the read or write speed is the same as the host disable LMU and with ATS supported in VM. In addition, if we want to use the direct P2P solution, we must pass through all the devices below one switch into the same virtual machine, because if the different device is passed through into different VM, and now we have already disabled the ACS, there will be some transmission wrong. Another thing we need to do is that the P2P solution can only impact the transmission path of the P2P transmission. For the DMA transfer to read or write the system memory, it will not change. The transmission, it also needs the LMU to translate the LVA to HPA like before. Another thing is that because we have modified the BIOS to ensure that the GPU bar address GPA is equal to the HPA address. So some operations in VM, such as PCIe rescan, will maybe change the GPA, maybe change the GPU bar address. So we must check this situation that if the GPA is not equal to HPA, we should do something such as pause the VM to ensure that the GPA must equal to the HPA. Okay, my part is all. It's up to Honghua.
Okay, thanks to Hexing. Hello everyone, my name is Hong Hao, and now let me introduce our work on high precision monitoring agents. In our internal AI large model tasks, we often need to get some info to detect bugs, which may rely on high precision monitoring agent. And these agents will read the PCI config space data and use perf to capture some useful information or connect memory bandwidth, which will cause a large number of VM exits and user space exits because of virtualization, just like the orange line in this picture. First, let me introduce PCI port I/O case. For example, in I440FX case, PCI config space read, which perform as PCI port I/O, will cause large number of VM exits and user space exits. Usually, when PCI config read includes two steps. The first is VM writes to I/O port CF8. The VM writes the BDF number and the offset of the device it wants to read to the PCI host bridge config register via the I/O port. Then it calls a VM exit. KVM captures the I/O port write and then determines that it needs to be handled by Qemu. So the vCPU thread returns to Qemu user space. And the Qemu write the data to the emulated host bridges config register, then return to kernel space. After that, KVM perform VM entry and the I/O port write finished. The second step, we will read the I/O port CFC, also causing a VM exit. KVM capture the I/O port read and it determines that it needs to be handled by Qemu. So the vCPU thread will return to Qemu user space again. Qemu emulator reads PCI config data based on its host bridges config register, which we writed. Then Qemu returns to kernel space and perform VM entry. And this PCI space read data finished. It takes more time than physical machine, especially in Qemu offload scenario. We have implemented an optimization solution that uses memory to cache on the KVM side to accelerate the VM's PCI config space read operations. For the first time, PCI config read, we cache the CF8 write as a key to the KVM and the CFC output read needs to do another 2 steps. One is update the CF8 key to Qemu. Another is cache the real value in KVM with the key. After that, we cache the BDF with offset and the corresponding data in KVM as key value pairs. Then we read corresponding PCI config space data will cost less time because we just need to fetch the value in our cache in KVM. No need to return to Qemu space unless the cache is invalid in some low frequency situations such as reboot or the device hot plug. After optimization, we found that operations like list PCI have cost less time, which 1,000 times of list PCI reduced from 28 seconds to 10 seconds. And now let me introduce our work on PMU pass-through. First is core PMU pass-through. When the virtual machine start up, we stop the CPU PMU's perf event on the core and restore it when the VM shut down. And we pass through the core PMU related MSRs to the guest, allowing it to directly read and write control registers and counter registers. Additionally, for NMIs generated on the host, we check the PMU's global status in KVM. If it's in an overflow state, we inject it into the guest and mask the NMI at the software level. When the guest acknowledges the overflow state, we trap the PMU's global overflow control MSR and then unmask the NMI. And the second is Encore PMU virtualization. We've used the Pyrovert to pass through the host's Encore PMU to the guest. For example, with Inter SPR's IMC PMU, the bare metal implementation uses discovery devices to get Encore PMU configurations information. We use Pyrovert shared memory to directly pass through this information from KVM to the guest. And the IMC PMU on SPR uses MMIO access. So we need to reserve a guest address range for it and set up GP to host MMIO MMIO mapping in IPD. A key limitation of Encore PMU pass-through is that it is digranularity, which causes difficulty to share among multiple virtual machines. Our future work includes 2 parts: upstream and resolve H2D and D2H virtualization declaration by DMA divert. And that's all. Any questions?
Have you looked into the recent work with Intel and AMD, also Google on the pass-through PMU?
Okay. Yes, I know. When we implement our work, we have not found the patches.
Okay.
Yeah.
So that's good to follow, right? So it's good to know that you like to use the PMU, right?
Yeah.
And also for Encore, basic question is there any use case you want to use Encore PMU in the VM?
Yes, we want to capture the memory bandwidth in VM. So we currently it is not realized. So we use the Encore PMU pass-through. Yeah.
Okay.
So I have one question. Initially, for that, you bypass the ACS, right? So when you said if the GPU bars is not what you actually expected, what are you going to handle? How are you going to report to the guest?
You mean how the VM knows the GPA of the device?
Yeah, because you basically force the GPA.
Yeah.
HGA, right?
We get the info in Qemu, and we use firmware config to pass through it to the OVMF, and we will modify the GPA in OVMF. Yeah.
Yes, but what if the guest modify that?
So it is a good question. We must forbidden these cases.
But what if that is a valid case?
What case?
Yeah, if, for example, Windows will modify the bars.
It will be a future work. Yeah.
Okay.
So 2 comments. First is on the first part where you talked about pinning the bars to the same physical address, or to passing the real physical address of the bar to your guest as a guest bar. We have patches pending that should go upstream in the next few weeks to basically achieve the same thing in cBIOS, EDK2, as well as Qemu, to basically do full segment population, like the whole topology, pre-populate that from user space already, from the VMM. In that way, not touch any of these of the bar mappings in initialization, which for the Linux case is safe. For Windows, screw them, whatever. The GPU acceleration case plus Windows is pretty much marginal. Nobody cares, right? You don't need peer-to-peer DMA with Windows. So which means let's collaborate, right? You have a solution. Maybe based on what you said, it sounds like you're effectively passing only the individual data into the guest, which is our old approach. That one does break often, so don't do it. Let's agree on the new path, or on any path at all. The second one is the port I/O acceleration. Cool. Great to do acceleration in KVM. It's just for this particular use case, it's the wrong path. The PCI config space access, the main reason why you're seeing so many PCI config space accesses is because Linux is not optimized for the virtualization case and always uses legacy port I/O when it accesses the lower end of PCI config space, even when you use PCI Express. Because with PCI Express, in theory, you would just have a memory view of config space that is exactly 4K, conveniently a page, right? That you could effectively one-on-one map as just memory into the guest. So with eCam and a guest that behaves sanely instead of what Linux does, you would be able to just have PCI config space be effectively free, which is the direction we should rather go towards. And that way your number doesn't go half, your number goes to 0.
Maybe our work is currently used in our internal, and that is a good question. Like you say, PCIe will use 4K config space, and that will be a future work. We think we should. For example, we need invalid the cache because when the MMIO. Yeah.
You don't need a cache if you also take ownership of the guest kernel, which I think in your environment is a sensible assumption. We can follow afterwards. It's fine.
Okay.
I have a rather naive question. How do you get the bandwidth between the network and the GPU, this P2P memory bandwidth? How do you measure
that? RDMA perf test.
Okay.
It's open source.
Okay, so that's all. Thank you.
everyone. My name is Dorin Dubasi, and I work at Red Hat in the automotive team. With me here is Matej.
Hi, I'm Maciej Hryca. I also work in the automotive team.
So in this presentation, we'll be talking about Virtio-gpu and where are we now. So we'll be focusing on implementing the Virtio-gpu device in the Rust VMM project, and we'll talk about like the problems we faced and how we worked on the device. So just to provide a little bit of introduction, one of our goals for the Red Hat automotive team in the virtualization space is to provide a virtualization solution for the Red Hat in-vehicle operating system. And in order to run Android on top of our virtualization solution for Rivals, we need to satisfy the Android reference platform requirements, which Sergio talked about yesterday in his presentation. And these requirements specify features that are needed for the Android automotive system. So it's a bit outdated, but still the requirements are still valid. So another of our objectives was to allow multiple automotive OSs to coexist by sharing the GPU. And since the Virtio-gpu driver that's in the guest need these Virtio interfaces to be able to access the GPU on the host, it kind of provides a minimal performance overhead. So just to show you a brief illustration, this is the architecture for running the Android Automotive OS as a guest VM. And the idea is that when the Android Automotive OS is running as a guest without any direct access to the GPU, it could use the open source graphics drivers like Mesa or GFX Stream, along with a Virtio-gpu driver and the device to provide the Android guest with an indirect access to the GPU for graphics processing. And this here is our architecture for Qemu KVM as a hardware agnostic hypervisor. So first of all, we have a standalone emulated Virtio-gpu device that's running the host user space. And this device will show up in the guest through the Virtio-gpu PCI bus. It defines how this Virtio-gpu device is exposed to the guest OS. Now, the application that's running the guest can make calls to the Virtio-gpu driver to render these graphics. And a typical example is, let's say, for instance, an application may use OpenGL or I think Vulkan APIs, which are supported by the driver. It would use it to make calls to the driver. And then this device would receive those commands in form of vert queues and translate them into actions that the host GPU can perform. And this is all being sent through the corresponding host libraries and interfaces. In summary, the Virtio-gpu device is a power virtualized graphics device and is based off on the Virtio specification standard. It's consisting of the PCI device, the driver, and the device itself. And it allows for both 2D and 3D graphics acceleration. And as we continue in this presentation, I would mention these terminologies more often. Okay, so let's go back in history. The interesting thing is we've had a lot of historical developments with Virtio-gpu, and the first development started with the inclusion of the driver 9 years ago by Dave Early and Gerd Hoffman, as this was one of the first steps that was taken towards having this hardware acceleration in the guest VMs. And then around the same time, they added the Virtio-gpu device with the accelerated 2D mode and the PCI proxy that was required for this device to be fully functional. And then moving onward came like more supports for the EDID, the context type initialization, and the UUID, that's the UUID-based resource sharing mechanism, and also the blob resource support. And there are many more developments which I would not highlight here. So where are we now? Many implementations of this device are beginning to exist. CrossVM itself has a Virtio-gpu device, and libkeyron has a Virtio-gpu device as well. Qemu has about 4 Virtio-gpu device variants, and we are currently working towards replacing the vhost user device version that's in Qemu. We're replacing it with vhost device GPU in the Rust VMM project. And currently this PR is still open, and the device code is based on libkeyron and the CrossVM Virtio-gpu code base. So We are leveraging on Virtual Renderer and the GFX Stream libraries through the Rutabaga crate for the rendering purposes. And I know you're wondering, okay, why did we add the GFX Stream component? We added that one because of the Android Automotive Reference Platform. It supports just OpenGL, ES, and Vulkan. So with this GFX Stream rendering mode enabled, we can have this GLES and Vulkan calls forwarded to the host. Another interesting thing about the device that we're currently developing is that it supports the already existing DBus and GTK display. So when this device is used with the DBus display, it would allow for Qemu to send the display information over the DBus system to an external process that's, in our case, we're using Snow Globe. And this would take care of rendering the data to the screen. DBus, although is a bit more complex than the GTK display, but our team is prioritizing using the DBus display because it has a lot of advantages, such as being able to be used in like containerized environments. And in cases where direct access to the display is not readily available, DBus is useful here. And also, our recent developments are based off on the Virtio 1.2 specification. So, why did we decide to implement this device in Rust? There were so many reasons, one of which was that the device crates would allow for compatibility with various VMMs, take for example Qemu or KVM, and it could operate as an independent process separated from Qemu. So the competition for resources between Qemu and the Virtio-gpu device would be minimized, and this would help to reduce the attack surface on Qemu. Another reason was that we could reuse the vhost user framework dependencies, and it meant that we could benefit from this framework to implement the GPU functionality. There's also the recent PR which we had worked on to add support for the Qemu's vhost user GPU protocol. And for obvious reasons, the benefits of the Rust language. So here, I want to talk a little bit more about the differences between the existing vhost user GPU device that's in Qemu and the vhost device GPU that's in the Rust VMM project. So the main difference is just boils down to these feature bits of Virtio-gpu. For the Qemu C version, it uses Virtual Renderer, and it has support for Virtual 3D mode, the EDID feature, but it seems to be lacking the blob resource support, the context type initialization, and the shared memory region. Whereas for the vhost device GPU that's in Rust, which we're developing, it allows you to switch between two backends, the Virtual Renderer backend and the GFX Stream backend. And it has support for Virtual, for EDID, and the context initialization feature. And as I speak, our team is currently working on adding the blob resource support and the host visible features. The related patches to enable it have been submitted to both Qemu and the Rust VMM vhost crate. So with this inclusion, we should have a fully functional vhost device GPU. And just for reference, I added a link in the slides for this device pull request.
The Virtio-gpu protocol requires the device to specify feature flags it supports. The driver in the guest can then acknowledge and use the ones it wishes to use. The vhost user protocol is designed to offload the Virtio device processing from the Qemu process to another user space process running on the host. This user space process is then responsible for implementing the device functionality as per the Virtio spec of that specific device. There are two sides to the communication: the front end, which is in our case Qemu, which is the hypervisor, and the backend, which is the device itself. In our case, it's the vhost device GPU. The messages are sent over a Unix domain socket, but also a shared memory is established. Implementing the GPU device as a vhost user device requires some GPU-specific messages in the protocol. The flow of the messages usually comes from the front end, where it sends them to the back end. But there are some requests we need the back end to request from the front end. So two other sockets are established, the backend request socket and the GPU socket. The backend request socket is general for more devices. And in our case, we use it to map shared memory regions. There is also the GPU specific socket, and we need that for display output and things related to that, such as updating the cursor location and cursor image. The Virtio-gpu device itself uses two Virtqueues. Virtqueue is basically a queue of buffers located in the guest memory. The device readable buffers containing the commands are processed by the device, and then the replies are written to writable buffers. Each Virtqueue consists of 3 parts: a descriptor table, available ring, and a used ring. The main queue in the Virtio-gpu device is the control queue. It's responsible for handling most of the commands. The commands come in form of requests, such as get display info or get EDID. And the device processes these commands and can return responses that contain the specific display info or the EDID information of the display. There is also the cursor queue, which is separate from the control queue, and it is basically a fast track for cursor commands. This is useful, so when you are moving the cursor doesn't lag behind as it waits for other commands to be processed. The Virtio specification also has what are called shared memory regions. These allow us to use zero copy operations on some buffers. We need to support these in order to implement Vulkan using Venus, which is the virtual render implementation, as well as GFX stream support in general. This requires some changes in Qemu to be able to use this over the vhost protocol, as well as the Rust VMM vhost framework. The advantage of implementing shared memory support is that in turn we can implement blob resources. Resources, in case of the Virtio-gpu, can reside even in GPU memory, but this depends on the type of the resource and the specific implementation. But in using normal resources, the data has to be copied from the guest memory, which is always the CPU memory, to the resource on the host. And if the device wanted to read the resource back, it has to be copied again. Implementing the shared memory regions allows us to implement blob resources, which have an operation for mapping the resources into the guest memory address space. And so this allows us to transfer data without explicitly copying it.
Okay, so for the device operation, how it works is that we have one worker thread, and when a new request is received, depending on the queue type, we have different handlers for processing the request. So there's a control queue handler and a cursor queue handler, which Matej already talked about the queues. So during the processing of these queues, it uses the reader and writer module of the Virtio queue crate to iterate over the descriptors. Although when we started working on the device, this wasn't how it used to work, because we would handle this descriptor processing inside of the process queue. But thanks to the recent addition by Matthias, we've been able to abstract it into the Virtio queue crate. So during the processing, the GPU command decoder processing, it decodes the GPU command and uses the Rutabaga interface to process the intermediate representations of these GPU commands. And in the end, a response is sent only after the command processing is complete. So On success, it will send a successful response, or on error to return one of the error codes. So to explain in details the processing of the GPU commands, there are some commands that need to communicate with the front end using the GPU communication socket. And when we're processing commands like the get display info command, what happens is that we're retrieving the display information from the front end through the GPU communication socket, and then we're processing the display modes. And for the flush resource command side, its goal is to take a specific resource and read its data, and then update the associated display with that data. There are other commands here which can be viewed in the PR of the vHost device GPU crate. For the rutabaga component side, what happens is that it can either initialize Virtual renderer or the JFX stream backend as a component, and it uses the Virtual renderer set flag method. So this specific flag would configure Virtual renderer for operating within the rutabaga framework. And it's the Virtual renderer backend there would now convert these GPU commands to the OpenGL API calls for rendering. And similarly, like the same thing happens for the GFX stream backend. It would convert it to OpenGL and ES, OpenGL, ES, and Vulkan API calls, and forward it to the host through the GFX stream libraries. And one thing to add is that the Virtual renderer backend can also forward the Vulkan API calls, but this may require like some Vulkan driver setup in the guest. And depending on the distributions, not all guests have that readily available. And this is the Rutabaga Virtual graphics interface here. It's designed to be portable across various VMMs, and this is why we adopted it as a layer on top of the GFX stream and the Virtual renderer in our backend. This VGI here relies on context types to be able to manage the different kinds of GPU commands that are issued from the guest. And these context types are basically different implementations that can handle the graphics commands, such as rendering with different backends. In the coming up talk by Sergio, he's going to discuss more about context. So while we were working on this device, we faced a couple of problems, one of which was that the rutabaga context could only be initialized once. And this was because the rutabaga context itself was tied to a single process. So due to the structure of the vHost device crate, which was different, it requires vRing to have the fence functionality. So one of the solutions we had here was to initialize the context on the first call to the handle event function. Another challenge that we had was that the rutabaga struct couldn't be transferred between threads. So this restriction was also due to the GFX stream and the Virtual renderer backend, because they had to be called from the same thread. And it kind of complicated matters as well with the vHost backend, because the vHost backend was using worker threads which could be called from different threads. And the solution here was to use like a thread local storage and stop the process when the guest shuts down. So since there's no way to reset rutabaga without restarting the process, we just stop the process, although like it's different for the other Virtio devices that's in the ROS VMM crate, because the process gets restarted automatically. And the other problem we faced was the rutabaga dependencies on the third-party modules, which by default crates that are distributed through crates.io shouldn't contain these submodule contents. So we're currently discussing with the cross-VM maintainers to actually have this dependence on Git submodules eradicated. So we would now just use the ROS source files and make it easier for other projects to use rutabaga.
Our main focus currently is Android support, and GFX Stream seems to be the preferred solution for that. Android actually also supports Virtual Render, but it does not support Venus, which is the Vulkan implementation in Virtual Render. And obviously we want the more modern Vulkan API to be enabled. There is also the possibility on horizon that the GFX stream could be used on normal Linux guests because a few days ago GFX stream got merged into Mesa. This is the guest side support. So we'll see how that works out. Virtual renderer is more suitable for virtualizing Linux guests currently. It can be used for OpenGL and Vulkan. Though, like I discovered that in Fedora, the Mesa that's built there doesn't ship the Venus driver. Our implementation of the GPU doesn't handle the rendering itself. It offloads that to the GFX stream or virtual render libraries, but we still run some benchmarks to ensure that we aren't doing anything slow. And actually, here you can see that when running glmark off screen, which is the second line, that the performance is about the same. But when running it on screen, it's quite a bit slower with the RASVM and vhost user GPU. And this is because we currently don't support like a fast path for the display output. And we could use the same calls in that the Qemu vhost user GPU uses. But these are not exposed through the rutabaga GFX interface. So we have to work on that. We also run Android benchmark where we compared 3D Mark Slingshot GFX stream against the virtual renderer, and it was about the same. But keep in mind this has the same issue where we copy the display output instead of using DMA buff to directly output it to the screen. There is no support for Vulkan in virtual renderer, so we don't really have anything to compare that to. In the future, we are looking into improving the scan-out performance using DMA buffs, so the display output isn't copied, and maybe add support for snapshotting. Currently, virtual renderer and GFX stream are used through rutabaga GFX, and we thought maybe specific RAS crates could be created for those. Here we have a demo of running Fedora using the vhost user GPU. We are using the dbus for display output and the snow globe application for actually showing the display. When starting the vhost user GPU, we configure the socket path and the renderer to use virtual renderer for Fedora. And then we configure the same socket for the GPU when starting Qemu. And we also specify a shared memory region, shared memory size, which is the size of the shared memory regions for mapping the blob resources. Once the guest boots, we can run OpenGL applications such as glmark. And we can also run Vulkan applications using Venus. But when I try to run VKcube, it first uses CPU rendering because the package of Mesa doesn't ship with a Venus driver. So you can override that, and when you build Mesa from source and use the built Venus driver, this works, but it's a bit choppy right now. So it might be probably related to the scan out that's copying the display output, and that slows down the whole pipeline. We can also run Android. Here in Snow Globe, we now enable emulating touch and show host cursor to actually see where the mouse cursor is. And we also started the vhost device GPU, but this time with a GFX stream. We use the start AVM script, where we also specify custom Qemu because of the patches that are not yet upstream. And we can run an Android image. And as you can see, Android boots, and we can run 3D applications. Yeah, but the performance isn't great right now. The benchmark is kind of heavy also, but the main problem is probably the scan out, which is being copied to the CPU. And also the call to copy it is blocking, which might lead to some issues, which we are working on fixing. And that's all. Thank you. Can accept questions.
Okay, thank you. So if you don't have any questions, I have one for you. How many of you use the existing vHost user GPU that's in Qemu? Okay, I see some hands. So maybe it would be nice if you help us try out the vHost device GPU and leave some feedback. The PR is linked in the slide, I think. Let me show you in this slide. So if you check the KVM Forum talk, you would see, you get the link to it. This one. Yes. Thank you.
So hello everyone, my name is Sergio Lopez and I work as a software engineer in the automotive team at Red Hat. And this talk is kind of a continuation of Dorinda Samatik's talk beforehand, but with a focus on the many personalities, many ways, many one languages that the Virtio-gpu device is able to interpret and talk. I'm also going to talk about a couple of real-world use cases in which we make use of those different personalities. Now, I think most of us working in virtualization are used to relatively simple Virtio devices. So you usually have your device implementation on the VMM, and then you have some kind of driver on the guest host, on the guest kernel. And basically, that's basically it. Basically, that's it for many devices. But Virtio-gpu in particular is sitting in the other side of the spectrum. So yes, you have your device implementation on the VMM, you have your kernel driver on the host, on the guest, sorry. But then you also need to interact with, and the host, you need to interact, as you, Dorin Damati explained, with virtual render, GFS stream, maybe rutabaga, potentially with the Mesa drivers on the host, potentially with a compositor on the host. And also in the guest side, you also need to interact with the Mesa drivers and the guest, the potentially a nested compositor, maybe a full compositor. So there are a lot of moving pieces involved in using Virtio-gpu, and to make things even harder, there are completely different ways of using this device. So to differentiate between the different ways in which you can use Virtio-gpu, it defines what they in the Virtio-gpu terminology is called contexts. If we look at the kernel source code, we can see like there are these 3 contexts, but the reality looks mostly like this. This is what you can already see in the wild. Some of these contexts are kind of well known relatively. So VGL and VGL2 is probably something that most people in the room has used once or twice. It was the original motivation for Virtio-gpu. It's a way of serializing OpenGL commands through the Virtio device. Some of them are perhaps lesser known, especially GFS stream before the previous talk. Probably because GFS stream until very recently was very tied to Android. So unless you were doing anything with Android, you probably didn't have any experience with them. But in any case, in this talk, I'm going to focus on these 3 ones, in Venus, cross-domain, and DRM. And that's because over the last year or so, I've been involved in different projects that make use of those 3 contexts. But before jumping directly into an explanation of those contexts, I would like to stop a minute to think about how it's possible that Virtio-gpu has so many different personalities, and it seems like it's growing every year. So if you look at the timeline that Dorinda Matei saw before, originally it was just VGL, and suddenly over the last years you get like GFS stream, cross-domain, various contexts. So how is that possible? And I like to focus on 3 features. This is a Virtio device. You have a couple of queues. Yeah, on those queues, one is the cursor queue, while the other is the command queue. I'm not going to go deep into that because we already have the previous talk. But if we focus on the command queue, we see that there are many of them, but I would like to focus on one particular command, which is execbuffer. Execbuffer is an IOCTL and also a GPU command, which basically allows the guest to send an opaque chunk of data from the guest to the host. So in practice, what this gives you is a unidirectional opaque transport from the guest to the host. Another feature I'd like to highlight is if a F resource blob combined with a host visible. So basically, this allows you to register a blob on the host and map it somewhere in the memory, in a memory region that will be shared between the guest and the host. So that way, both the guest and the host can share data between them in a seamless way without having to copy it around. And what this gives us is the ability to implement rings, queues, to map file descriptors. And as a side effect, it also means that the exec buffer becomes a bidirectional opaque transport. Because yes, the guest can send opaque chunks of data to the host, but that now the host can reply using shared memory. So now exec buffer becomes a 2-way bidirectional transport. And the 3rd feature that I'd like to highlight is fences. Fences are mostly built on top of the conventional Virtio communication mechanism. And what basically allows you to do is to have pullable objects. So by combining these 3 features, you can basically implement whatever kind of protocol you want to do on top of that. I mean, if you need a pipe, just use exec buffer. It's already a bidirectional opaque transport. If you need to pull on the pipe, you can do a fence, and then you can pull on the file on that pipe that is modeled on top of Virtio-gpu. Do you need to share a file descriptor, register it as a blob, and put it on shared memory, and then you can share between both devices, both contexts. So in the end, I don't know if it is one on purpose or not, because I haven't followed the GPU history, development history so closely. But by having these three primitives, you can basically lay on top of that arbitrary protocols. So it kind of has become this kind of omni device. It's a Virtio device. You can put anything on top of that. Okay. Having said that, let's jump directly into the context themselves. So the first one I like to talk about is Venus. So Venus is basically a transport for serializing Vulkan commands, Vulkan instructions. Now, I'm not an expert on OpenGL nor Vulkan, but I have been told that Vulkan is more friendly towards serialization than OpenGL, basically because it operates at a lower abstract level, so the semantics are clearer and simpler and easier to serialize and marshal. Of course, it makes heavy use of resource blobs, so there is a significant amount of shared memory between the guest and the host. Basically, every BO is going to be a resource blob shared between both contexts. And the main use cases for this is, of course, Project Borealis, which is the main motivation. This is a project from Google for bringing games to Chromebooks. So on Chromebooks, there is this Linux context, which is actually a VM. And this is in this VM is where they run games. So of course, they needed a way to expose GPU acceleration to the VM. And they developed Venus for this particular purpose. Another use case, which is one of the first real-world examples I want to give about the power of these contexts of Virtio-gpu, is Podman Desktop and the need to enable macOS to run GPU-accelerated containers. So long story short, some months ago, we came up with the necessity of basically doing large language model inference using running containers on macOS. But of course, containers on macOS are Linux containers, and since there are Linux containers, they need to run in a VM. So we needed a way to expose some form of GPU acceleration to that particular VM. And the problem in macOS is that the hypervisor framework and the virtualization framework has support for GPU acceleration, but only for macOS guests. It's not exposed to Linux guests. And even if it were, there are no open source drivers, and there is no open source user space drivers either for managing that, that GPU acceleration device. So we needed to come with something, and we came up with this. So basically, what we do here is we have a Linux VM guest, we have a Virtio-gpu device, and this Virtio-gpu device is able to talk the Venus context. So then we have applications that may be using OpenCL or maybe using Vulkan as a backend. For instance, Llama CPP has not one but two Vulkan backends. They have one is called Vulkan and the other that is called Compute with a K. And those will be compiling the shaders for the workload using through Mesa into SPV. These SPV shaders will be sent using Venus for coordination to MoltenBK. And MoltenBK translates these SPV shaders into metal shader languages. Eventually, those metal shader languages are again compiled again by the metal framework in whatever language the GPU consumes. And even though this may seem like a very long pipeline, on a first thought, you may think that is quite inefficient. In practice, compiling the shaders is something that happens just once at the start of the workload. And everything else that happens afterwards goes through shared buffers, through those resource blobs, those shared memory regions we talked about before. So in practice, once you have set up the context of the large language model, everything that is going to happen through shared memory that is visible both to the guest and the host. And in this case, it's also memory that comes directly from the GPU. is actually device memory. That is first mapped into the hypervisor, into the VMM, which is in this case is libkern, and is then injected into the application using the hypervisor framework API. So what this means is in practice, the performance of this environment is practically the same you get in the native context. It's almost indistinguishable. Okay, moving on to another context, I would like to talk a little bit about the cross-domain. So most people, or most of us, using virtualization and using any kind of display output are used to work with frame buffer. So if you run Qemu by hand and you run any VM, you will get this window, maybe GTK window is the old window that has a frame buffer. You get to see how the guest is booting. Eventually, you get to see probably some kind of compositor. But the thing is that drawing in the frame buffer is not always the best approach. On one hand, it's possibly not the best UI if you are not interested in running a full operating system. If you want your VM for running just one application, or for, in this case, for running one game, having to do that through with a full frame buffer is not the best approach. And also, the performance is potentially worse, because the best scenario, if you want to draw in a host window, is to actually grab to draw directly in a surface of that host compositor. And that's something that can be done. You can export using DMA buff that surface from the host compositor and pass it through to the guest and have the guest draw directly into that. But to be able to do that, you need to somehow coordinate the host compositor with the guest compositor. And for that, we need also a way for both compositors to communicate. And here is where cross-domain enters the game. And this one is one of those things that kind of reinforce my argument that this B-dio device has become like the omni device that's able to implement any protocol. Because in this case, it's basically a way to implement a WLAN over Virtio-gpu, basically. So you can have an nested WLAN compositor on the guest, such as Sommelier, communicating with the host compositor on the host, and then run applications on the guest that appear like regular windows on the host. So it gives you better performance, as I said before, and it's also potentially the best UI. Lastly, I want to talk a little bit about DRM native context, which is quite a newcomer into the Virtio-gpu world, and it's quite an interesting one. So we know there are contexts that serialize OpenGL calls. In fact, there are two, VirtGL and GFX stream in the GL variant. There are also contexts that serialize Vulkan commands. And in this case, with DRM native context, we go even lower. So with DRM native context, we are serializing directly the IOCTLs directly. And now the problem of this approach is that, of course, the IOCTLs vary from one GPU driver to the other, so they are not the same. Which means that you need to have, on one hand, you need to have a Mesa driver that is aware that it can serialize the IOCTLs and push them through Virtio-gpu instead of opening the actual GPU device it expects to be opening. But on the other side, on the host side, you also need a virtual renderer that is able to unpack those IOCTLs that is receiving serialized and execute it on the host side. So far, we have two implementations that are already upstream. The first one, which was developed by Rob Clark from Google, who was the one who invented this mechanism, which is the MSM or FreeDreno driver. But recently, we have got a new one, which is the one for AMD GPUs. And there are also two work in progress drivers, one for Intel devices, and another one for Asahi, which is the one I personally contributed lately. The use cases for DRM native contests are, again, in theory, Project Borealis, but I mean, in theory, there could be Chromebooks out there using that are based on Qualcomm boards, that they have a FreeDreno drivers, and that using DRM native context to have better performance than Venus. But I have not formal confirmation that this is something that is actually done on the wild. In theory, it was for that, but I don't know if it's being used or not. And another real-world use case, which I've been involved with, is running commercial games on Asahi Linux. So the thing the problem with commercial games and Asahi Linux is that, of course, Asahi Linux is targeting Apple Silicon devices, so it's ARM64, and most commercial games only provide x86 binaries. So this means that we need at least a fast user space x86 emulator, because otherwise it will be impossible to run them. A second problem is that Asahi Linux is a 16K page distribution, mainly because most devices in the hardware expect it to be like that, and the Linux kernel doesn't really support having dual pages. It's true that, for instance, Darwin on macOS is able to do that. It may have processes that are 4K or that operate at 4K granularity, and processes that operate at a 16K granularity, but this is at least not the case for Linux for now. So we needed to run a way to run a 4K kernel on Asahi Linux without replacing the host kernel. And of course, the obvious option is to run it in a VM. Now, this generated a second problem, which is VMs doesn't have direct access to graphics, and using Vfio is not an option because this is an embedded GPU on a board, so you cannot delegate it to a VM. So we needed to use something, and in this case, the solution was using Virtio-gpu with DRM native context for better performance. Now, I'm trying to go and do a live demo of this, of using DRM native context with KVM, Qemu, and on this laptop. It's going to be live demo with one hand, so please bear with me. Okay, so this is Asahi Linux. We are running a regular kernel from the Asahi Remis, a 16K kernel. And what I'm going to do is I'm going to start a VM using krun. Krun is just yet another utility that has spawned up using libkrun, has VMM, that's designed specifically for this particular purpose. So it uses the root file system, has the same file system for the guest, and it also starts up Sommelier and other needed tools to actually start using running games and using DRM native context. So I'm going to start it up. Here is it. Okay, this is a freshly started VM, which is running a different kernel than this one. It does have a DRM device, and we can see, if you remember from the previous talk, we can see that we have support for BGL, resource blob, host visible, context init, all the features we need. And of course, we have access to the /dev/DRI device. So let's run some benchmarks, shall we? So this is the terrain benchmark of GLMark with a 3-second duration. It's really quick, but this benchmark is quite stable, so 3 seconds will be fine just for its illustration purposes. This is running inside the VM, and it's using DRM native context, and we get a score of 290. Now, let's run the same benchmark, bare metal. Again, 3 seconds, and we get 304. So, I mean, on the VM, we are getting like 95% of native performance, so it's fairly good. But of course, running benchmark is fine, but let's run some games too, which is the actual purpose of this. So this is a game, an indie game that is called A Short Hike. It's a cozy indie game that is only available for x86, so we are running it using a crash, of course, because it's live. This is what you get if you do live demos. Okay, now it's getting there. It's the first time it crashed for the 100 times I run it during this week. It needs to be this one. So this is a 3D game built using Unity, and it has a number of post-filtering operations to look like retro, but it's actually a 3D game. And as we can see, we are getting a fairly decent amount of FPS, like over 160. So it's perfectly playable. I mean, there are no graphic artifacts. It's working perfectly fine. We can go with something more expensive. Crossing my fingers. This is another indie game. It's more expensive in CPU terms because it's drawing a more complex world. It looks small because I wasn't sure about the size ratio of the external output, but it can also run full screen. Oh, I forgot to put, sorry. Let's run it again with Gallium to get the FPS. Nice when it's not going to start for sure. Getting there. It is there, okay. Okay, we're getting over 100 FPS, so fairly decent and definitely playable. So I think this gives us a rough idea of how this native context enables actually to run these games on a VM. I cannot run commercial games here, basically because this MacBook only has 8 gigabytes of RAM. But if you want to see more complex and commercial games about the running here, Asahilina did a live stream. He tested a number of them. You can download this. There are links on the slides when you want to check it out and actually confirm that you have quite a bunch of commercial games. Many of them quite expensive in CPU terms and GPU terms and work perfectly fine at 60 FPS. Yeah, you can run Crisis and yeah. So it's good. So I think that's all I had. Any questions?
So how about the Linux host? So can we run this cross-domain and also native context on the Linux host?
Running cross-domain on the Linux host, but
I mean, Asahi Linux is on Mac OS hardware, right?
Yes.
Sorry. Yeah, I mean it's other normal like x86 machine or other hardware. Can we run that?
Can you run that on x86 hardware? Yeah. In fact, they probably makes less sense because I mean here we are trying to cover two challenges. The first one is that these games are x86 games, so we need to emulate them because we are running on an ARM architecture. And the other problem is that also we needed a VM because we need to run a 4K kernel on top of a 16K kernel host. But if you wanted to have additional isolation on x86s, this should work perfectly fine. Yeah, the only requirement is that you need to have a GPU driver that is supported by the DRM native context, which, as I said before, there are those four. MSM, AMD GPU, Intel, and Asahi. Well, Asahi for x86 doesn't make much sense, but one of those three.
Okay. Another question is DRM I control interface will be sometimes changing, right, for different vendors. So we have to handle for different kernel versions, like for different interface. Okay.
Yeah, that's kind of one of the challenges of DRM native context over other contexts, because I mean, for Vulkan, you don't expect the Vulkan to change behind your feet, because I mean, if it changes, it's going to be an extension, so you can prepare for that. For OpenGL, it's the same story. For DRM native context, that means that you have to have the virtual, Mesa, and the kernel driver always in lockstep. So you need, every time you increase the UAPI, you need to coordinate all three updates. This is especially a challenge for the Asahi driver because it's not yet upstream. So that means that every time Asahi needs to update this kernel or Mesa or virtual render, it needs to update all the three at the same time. But yeah, that's definitely a challenge.
I mean, will there be any capability check or some protocol to make sure we have the same correct binding? Or?
Yes, during the context of the initialization of the context, you exchange data between the guest and the host. So one of the things it does is verify that the UAPI is aligned between the kernel, well, the different components, the guest kernel, the guest user space, the host kernel, the host user, and the host virtual renderer. Yes, it's verified.
Thank you.
Welcome.
How stable is Asahi's API now? So you relies on this API now, right?
Well, instead, when you try to do a live demo, it works very well.
I mean, the interface stability. So you rely on DRM interface, so it will break if the upstream driver changes, right? So how is it going to change again, or is it?
Yeah, right now there are no UAPIs guarantees for Asahi. So the thing is, until the GPU kernel driver has been upstream, the UAPI is not guaranteed to be stable, and it will change and it will break user space, which is why the reason why we need to update all three components at the same time. But when it eventually gets upstreamed, we expect it to be stable.
Okay. Right. Thank you.
Welcome. No more questions, so thank you all.
Hello, my name is Alexander Gordeev. I work in Qualcomm, and today I'd like to discuss the draft Virtio video specification. It's a rather long formal text, and with this presentation, I hope to make it easier to digest to potential reviewers, and I hope maybe you will want to review it later and maybe even use. Yeah. First, I'll talk about the scope of the specification and list some goals. Then I'll provide an overview of the current status. And then I'll dive into the main use cases and some design decisions, while also trying to compare it with some major video APIs. Yeah. First of all, how many of you are familiar with like any video API? I'm really curious. Oh, nobody. Well, I expected that. That's why I'll try to like describe the problem a little bit. So yeah, how the video streams are compressed in general. There are two main sources of redundancy in the video streams. First of all, the spatial redundancy, or like finding similarities in the nearby pixels within a single frame, and also temporal redundancy. So finding similarities between contiguous frames, and so first thing is something like PNG, and the second thing is basically what you can see here. So there could be some different frame types. The first doesn't depend on anything. The P frames depend only on the previous frames, and B frames depend on both previous and future frames. And yeah, this creates a lot of trouble to the API developers. And yeah, because first of all, now we have to decode the frames in different order compared to the display order. So there is now decode order and display order. Yeah. Yeah. So there are two main types of video APIs: stateful and stateless. Stateful APIs look like a black box. You just provide some input data, and you get output data on the other end. It stores all the state between the frames for you. It parses everything, and it will also keep the reference frames. Remember the previous slide. And the stateless APIs will require you, well, the client, to parse the bit stream, like take only the computationally heavy parts, provide all the context, all the state, all the references with each frame, and supply this to the hardware. So Virtio video spec is a stateful API because there is hardware that provides the stateful API, like we have in Qualcomm, and one can implement a stateful API on the driver side on top of the hardware providing stateless API, but other way around doesn't work. Yeah. So why would we virtualize video hardware? Obviously, to offload the heavy processing from the CPU to the hardware. How do we know that we do it right? So there are some tests that we can run, like Vfio and compliance tests, Fluster, and Android CTS tests. Yeah. Okay, so the next goal is that we should try to saturate the hardware. I mean, it should not wait unreasonably. And also, we try to keep latencies low. Next goal, we obviously want to implementing the Vfio guest driver on top of this Virtual Video spec, like Virtual Video device, as straightforward as possible. And also we want to keep it simple and easy to understand and extendable. So it is not an easy task, in fact. So because there are a lot of things that can change on the fly, and also because of all of these reference frames, and there are many codecs, different codecs, and some weird corner cases, and yeah, there are nice overviews that you can see for the weird corner cases. So basically, our solution is to gain experience and learn from other APIs, and try to make it as best as we can, as good as we can. So there is quite some history already. Currently, we are at draft version 9. It's on the far end, and I already have enough internal feedback for draft version 10. But please do not hesitate to review it, and maybe you will shape the version 10. The Virtual Video driver implements draft version 3 with some parts of version 4, so it definitely has to be updated, but it is in production since 2021, actually. So Virtual Video was initially very similar to Vfio 2, in fact, with some parts taken from Virtio-gpu. Well, I mean, I think they even took a lot of code from the Virtio-gpu driver back then. It was not me. Yeah, except that compared to Vfio 2, the hardware capabilities were always provided in a single Virtio exchange. Over years, it was significantly simplified, sometimes oversimplified. Then last year, the draft maintainer decided to start from scratch with Virtual Media, and so they wanted to use Vfio 2 user API directly with minimal changes. Yeah, well, makes sense to me for their use case. For our use case, it didn't really make sense. So I volunteered as the new maintainer for the Virtual Video, and since then I brought back some complexity, but I took a lot of the ideas from GStreamer, in fact, because I know it quite good. Yeah, that's what I have done, have practiced for years, and I'll try to show why I did it, why I thought that it is better. So I'll try to go through use cases, but I'm sure I will not have enough time for everything. But so I'll start with the important things. How would we process a video stream? Of course, we'd like to avoid copying the big buffers. So we need to share them with the processor. Yeah, relocate them and share with the processor. Then we fill input buffers on the left. Then some magic happens, and we receive output data on the right side. Yeah. Actually, there could be multiple sets of output buffers. For example, an encoder could provide several resolutions, like medium, high stream, and low resolution at the same time. This is like good for like scalable video coding, for conferences. Yeah. So usually the hardware supports multiple independent stream, and they can run simultaneously. Like I try to show it here. But we can already see several queue-like objects on this picture, and now we need to somehow map them to the virt queues. So it's it's already clear that in some cases it is better to have as few virtues as possible. But while in other cases we can, like if we have more like memory or whatever, we can it can make sense to have more of them. So I'd like to start small with the only 2 virt queues, one command queue that queues the buffers to the and other commands to the hardware, to the device, and with event queue that basically delivers the delayed responses to the guest. It's called delayed responses because it's basically they are kind of independent, and this is kind of required because of the reordering. Otherwise, we can get stuck. Yeah. So how does a video stream processing look like in other APIs? So my main references here are Vfio and GStreamer, and I also said that I prefer some of the solutions in GStreamer. So yeah, please don't think that I hate Vfio, but I will complain a little bit. Yeah, so it is done somewhat similarly in Vfio and GStreamer. There are like 2 queues. Yeah, well, for the simple case. In Vfio, it is called output and capture. If you want to have multiple capture queues in Vfio, well, as far as I know, you can only do this with multiple sub-devices and by using media controller API, which requires separate media device nodes in the guest, and yeah, it's quite complicated, I think. So it's basically for setting up topologies for very complex devices, in fact. For the Virtio video, if you want like have several output sets of resources, as I said, I think it looks like an overkill. Maybe we just need more output queues. Then we can build more things on top of that, like we can use fences, and probably, yeah, that would be already enough. But in some cases, there indeed might be some need for complex topologies. Yeah, and I like how GStreamer allows multiple source and sync pads, or sync and source pads. Yeah, that's kind of the idea. Yeah. So before we can process anything, we have to set things up. This is done with parameters. In most cases, the parameters change rarely, and also they usually can survive a reset or drain operation, which is basically some queue management. I'll get back to that later. Yeah. So I don't have time to name all the parameters, but I'd like to classify them. So there are multiple ways to look at them. First, some parameters define how the coded or encoded stream behaves. These are coded format, like bitrate and profile and level and so on. And there are parameters that define the raw stream, like raw format, format modifier, maybe for tiled or compressed formats, then resolution and some hardware alignment requirements. And yeah, obviously we need to set up the resources or the buffers, actual buffers. Another way, like to look at each parameter, basically each parameter has some capabilities, like the device has some supported ranges for each parameter, and for each stream, this will be a single value, right? So on the left, there are examples of the ranges of the for every parameter, and on the right you can see the like actual values for the particular stream. Yeah. So I try to visualize it here. So let's imagine that on the left we have like a multi-dimensional space of all possible values of coded parameters, where each parameter is a single dimension. And the same thing on the right for the raw formats. Now, the figures in these spaces would represent the device capabilities. And if there is an arrow, then that means that the hardware can basically convert from some point from one figure to some point to in another figure. And like a stream would like represent the points in these figures. I think, yeah, it's the most intuitive and natural way to think about the parameters. So, how are the parameters represented in Virtio video? So, one of the goals was to minimize the latency. So, we want to get the capabilities and also get and set values using as few commands as possible. So I couldn't find a better option than TLV, which is a type length value. Basically, it's a very simple format. You just have type, you just have length, and arbitrary length value. And it's also very widespread. Yeah. So here, capabilities are represented on the left with a number of TLVs of type coded set, like you saw on the previous diagram. Then there is a number of raw sets and a TLV of type link that establish links between them. The values on the right use the same TLV container types, but but there would be only a single, like for the coded queue, there would be a coded set, one coded set, and for the raw queue, there would be one raw set. Yeah, this way we need only one command per operation. Let's look inside the sets. Yeah, so with capabilities we have the ranges. With values we have the some individual values, but you can see that the same types from like TLV types are used in both. Yeah, on both sides. Note that we can use Vfio to control IDs in the TLV types. So there is like a block that changes the type space, right? I like how the Vfio controls are defined. Like there is a huge page with all of the Vfio controls. It doesn't make sense to redefine them. With like there are some minor exceptions, but in general, yes. So they are reused here. Yeah, and finally, some parameters can affect the resources or the buffers, the shared buffers, and other parameters will not affect them. So when we handle the parameters that affect the resources, we should be extra careful, of course. And yeah, the other parameters can be changed easily on the fly without any precautions. So how do capabilities look in other APIs? Yeah, in GStreamer, I can start with GStreamer. So in GStreamer, we have non-fixed GST caps. Here's an example. In fact, it looks very similar to Virtio Video's TLVs, except that there are no explicit links between like these lines, I would say, within the GST caps. In Vfio 2, it is rather complicated. So first, you usually get yeah, there are a lot of I/O controls that you should run. Oh, and yeah, then there are a lot of enumerations. It's when you like run an I/O control with ID 0, then with ID 1, and so on, until you get an error. And also, like these lines are dependent. They depend on each other. And basically, you cannot just put all of them at once in the virt queue and just wait for the response. You have to, they are dependent, yeah. So this can lead to increased latency. Yeah, values in other APIs. It is similar with values. In GStreamer, we have fixed GST caps with the same keys, like in TLVs. And in VFOL2, there are again a lot of I/O controls. Yeah, it's interesting that it is done differently with extended controls. It is somewhat even similar. So actually, struct VFOL2 X control is really similar to a TLV. There is also a type, a length, and a union with a lot of value types. Yeah. So actually, I even hope that maybe VFOL2 can adopt the this TLV format. So first, we can think it as an extension to the extended controls. Like first we extend it to the capabilities, then we extend it to other parameters, not only the controls in VFOL2 terms. Yeah. So next, it's also important how we set the parameters. There are two main ways to get and set parameters: in band or like serialized with the flow of buffers, or out of band, and like it can go ahead of the queue. It is okay if you don't need fine-grained control to which buffers the parameters are going to apply. In this, if you don't need that, you can do it out of order. But sometimes it is necessary, usually with encoders. Yeah, and also like modern APIs like Android Codec 2 actually required. So I think it is better to. It is necessary to have a way to set them in band. So yeah, if we serialize them with the buffers, we can have fine-grained control, like to which buffers will apply the parameters. Yeah, so in fact, in Virtio video, it is kind of a default. Let's also look at dynamic resolution change. So in many cases, the parameters can change on the fly. For example, the resolution. When you, I don't know, when you have a conference and the bandwidth, network bandwidth suddenly changes, and you have to switch to lower resolution. Or you watch YouTube, the same thing, right? So it is basically a custom case of in-band parameters because they are stored within the bit stream in the buffers, and when decoding, yeah, we can. It is used here, and basically it is the same procedure. Yeah, note that the dynamic resolution change can also change the parameters. For example, if the resolution goes from this figure, we maybe want to jump to another figure, right? Yeah, so in other APIs, VFOL2 has many I/O controls to get and set various parameter values. All of these are out of band, and there is a special API for setting parameters in band called request API, and it's also a part of this media controller API. It is rather complicated, and it's basically not a default, and it only works for the controls, which is like a limited part of all the parameters. And there is a special procedure for handling resolution changes. In GStreamer, we just have GST event caps. Well, there is also caps negotiations, but basically you just receive GST event caps on the sync pad, then you send on the same, well, again, GT event caps on the source pad, and you're done. It's all in band. Yeah, I'm not going to cover drain and reset. Sorry. If you want, you can look at that later from the presentation. I think the Virtio video spec is now clean. It provides easy and consistent solutions in common cases. But yeah, as I said, there would be also version 10 to clean up it even a little bit more. This is mostly the result of taking the best from Vfio 2 and GStreamer. I don't expect that Vfio 2 can somehow become more consistent here because they have a lot of legacy. Yeah, that definitely can happen. But that will, I think, require a lot of time, and somebody has to do it. Unfortunately, we don't have enough resources to also change it right now. Yeah. As I said, there is the Virtual Media device specification. It uses Vfio 2 directly with few modifications. I think, yeah, there is certainly a use case for that. Like, as far as, well, when I think about it, I think, yeah, when you have Vfio 2 on the host and you just want to get it in the guest, yeah, certainly it makes sense. But I'm coming from automotive, and I don't remember a single case when we just had the Vfio 2 on the host, and yeah. So there are also other things to consider, and yeah. Thank you. I hope it makes sense to you, and please review Virtual Video or even both specifications. And yeah, if you review version 9, then the feedback could be addressed in version 10. Do you have any questions?
You talked a lot about the specification. What about an implementation? Is there something out there?
Sorry, the last part?
Is there an implementation already available that some patches that are on some list or somewhere in the public?
Yeah. So there is a Virtual Video driver in the public, developed by us, and there is also, I think, an Virtual Video device implementation in Rust VMM, as far as I know, which I'm not sure if it's supported now, but yeah, probably it works. We have our custom proprietary implementation, unfortunately, right now, and but yeah, let's see. Maybe it can change in the future. Maybe one more question. Okay, thank you very much. And yeah.
Hello. I'm glad that everyone made it back from the pause and from the group photo. Yeah, so we're going to talk about the KVM backend in VirtualBox. This is Martin. I'm Julian. There we go. 2 disclaimers before we start with the content. VirtualBox is a trademark owned by Oracle. We are not Oracle. We also have no affiliation with Oracle. And the second trademark is that this is teamwork with Thomas Prescher and Stefan Kober and Sebastian Eidam. I think you also did stuff, Virtio. And many other colleagues at Cyberus, and we are just the lucky ones that got to present here. What are we going to talk about? Super quick introduction what Cyberus is. We're going to talk about why we did this. Then I will hand it over to Martin for all the cool technical low-level things. And then our talk will be over. So who's Cyberus Technology? For those of you that we didn't meet in the bar and told this before, so we're like a tiny company in Dresden with 25 people. We currently do lots of things in the realm of cloud hypervisor, VirtualBox, KVM. We like to use NixOS, we like to use Rust. So if any of this seems interesting to you, come find us afterwards. Then, if you're wondering how we test all of this virtualization code that we write, there was a talk yesterday by these fine gentlemen over there about testing. It's also worth watching. Okay, with that, what is VirtualBox? VirtualBox is a user-friendly virtualization software that has broad host and guest operating system support. VirtualBox runs on Windows, Linux. It may run on Solaris as well, at least it used to. Also, inside of VirtualBox, you can run everything from DOS to Linux to modern Windows 11 guest. It has all the nice features that you want to use in a desktop virtualization product. It has dynamic display resizing, clipboard integration, shared folders. You can drag and drop files. And in general, it's a really nice out-of-the-box experience. And this is also why it still has a lot of users. Especially non-technical users like to use VirtualBox, and it's in surprisingly many products where you wouldn't think it is in. Here, lots of people use Qemu, libvirt, and maybe also GNOME boxes, and you may ask what's the relationship between all of this. So in general, if you use the stack on the left, you get basically the same experience as in VirtualBox. You just have to piece it together out of many different projects, and so there's like the bazaar style of development, and VirtualBox is more like the cathedral, one huge repository with everything, and it works without fiddling. So far, lots of positive things about VirtualBox. So why are we even doing something in this area? So since VirtualBox is pretty old, they actually started out with their own hypervisor. They ship a third-party kernel module that implements the whole VMX stuff and AMD virtualization. This has historically had quality issues, so you can find people ranting about it on the Linux kernel mailing list. It is very different from KVM, how it works. So basically, VirtualBox uploads a lot of code into the kernel that also can do lots of emulation code directly in the kernel. This is not something you would design like this anymore. And of course, the main downside is that you can't use it together with KVM. And KVM, people want to use KVM. The other thing is, since it is a third-party kernel module, you have to use DKMS or some other horrible technology to use it. This is annoying for users, but also for distros, and in general, you don't want to have this. So what you want to have is basically the VirtualBox user experience, but without all the hassle of custom third-party hypervisor. This is obviously where KVM comes in. KVM is a really great fit for VirtualBox. It has many features that VirtualBox does not have, for example, all the modern interrupt virtualization features like APIC-V and AVIC. KVM has all of those. KVM has a way more complete set of Hyper-V enlightenments to make Windows guests fast. It has a pretty robust security story, maybe not perfect, but definitely better than the VirtualBox hypervisor. And of course, KVM just chips in all the Linux distros, it's just there. So, and this means that if you are someone who likes to use hardening patches like GR security packs, you will have no problem if you use KVM, and you are in a world of hurt if you want to use the VirtualBox hypervisor. And now the question is, how do we marry the two worlds, VirtualBox and KVM? So VirtualBox already has multiple backend types. So Oracle has discovered that also on other platforms, it's really nice to be able to use the native virtualization API. So in addition to their original hypervisor backend, the HM, they introduced like the native execution manager in the code base. And this is what enables VirtualBox to use the default hypervisor of a platform. And they have like proof of concept NEM backends in the code base for Hyper-V, macOS, and KVM. But the KVM one is incomplete and broken. So you cannot enable it. You would have to fiddle in the makefiles, I think, to enable it, and then it will just not work. So what we did, obviously, is we set out to fix it. We started last year. If we had a longer talk slot, we could talk about all the amazing things that we did. So we fixed the interrupt handling in it. We fixed the timeout, the timing handling in it. Then it started working, and then we went to the cool stuff. So we made it use the split IRQ chip. We made it use split IRQ chip in KVM for performance, and we also enabled all the KVM Hyper-V enlightenments for VirtualBox, so Windows VMs run really nicely. But one of the major issues we had is we also tried to enable virtualization, nested virtualization support. And initially we thought, well, we tell KVM to turn on the VMX CPU ID bit, and we do some VMX MSR whitelisting, and there we go, nested virtualization. But this turned out to be a somewhat longer story with some interesting bugs. And for this, I will hand over to you.
Thanks, Julian. Yeah, initially we try to just enable VMXE and the CPU VMX flag and some MSRs. And actually, Linux works in Linux. So this was the easy part. But we also have Windows. So, but before we start the deep dive, let's talk about the terminology again. When it comes to nesting, we have a guest, which is called in our talk level 1 guest, and the one which is booted inside the VM is the level 2 guest. So now let's start with a deep dive. Ooh. Can you? Yeah, thank you. Now the issue. In certain scenarios, we get with the level 2 hypervisor the issue that the Windows VM crashes with the kernel mode exception. Actually, after some debugging, we found that the main issue started in the TLB flush routine of the global page tables, especially at the instruction move CR to rex, move rex to CR. Sorry. There caused a general protection fault. So what we then we after finding this, we investigated deeper and deeper and just used our own guest tests. Did test suites that we used for our own hypervisor when we developed it some years ago, and now we have restarted it and re-implemented a new test that just checks the values for CR4 in the level 2 hypervisor, level 2 guest, sorry. And yeah, this is what we have done then. We found the root cause. In certain scenarios, when we run the VM a while, we discovered that the CR4 value changes out of the blue. We didn't even know what is going on there. So what we've done is that we use signals to interrupt the level 2 and level 1 hypervisor to deliver timing events and device interrupts and something else. And what we found is that after some exit, which is caused when the level 2 hypervisors, level 2 guest is run, the KVM in the KVM run register, KVM run struct is the level 2 state. That means that, in our case, also we mark control register values as dirty every time we enter the guest, because we thought that it's inefficient, okay, but it should work in the meantime. So, but this is not the case. In the case of KVM, it is that way that if we get a VM exit in the level 2 in level 2 guest, then we just have also the register state of level 2 in the KVM run struct. And we doesn't even know that, so we just write the other value of the level 1 value of CR4 again to the SREX. And actually this caused the general protection fault, because at this case we enable CR4 VMXE, so we enabled VMX for the level 2 guest, and this causes a general protection fault. Also, we have after finding this issue, we also have seen such issues in Qemu. We have a ticket for that.
Maybe a quick. So I filed this bug in Qemu like 2 days ago. So in Qemu you can trigger the same issue with safe VM. It's really weird. So if someone wants to talk about it afterwards, it's a good topic.
All right. Okay, how did we solve this issue? At first, we looked at the Qemu code and checked whether it could be an issue. So, and we afterwards just marked not the control register value is not dirty anymore, and just change it if they really change. And this helped us a lot, and we could get working Windows in Windows. Yeah, but from our perspective, this is just a workaround, not the real fix. So we submitted a patch where we fixed the behavior which got rejected, but enabled really good discussion on the mailing list, on the KVM mailing list. And we got supposed to get a new solution for that, which was the addition of a new flag in the KVM run struct, which indicates the execution level, which is basically the guest which is executed in right now. Okay, this one is also submitted to the mailing list, and we were able to get it merged. And it will be available with Linux 6.11, which is released right now, I guess. So yeah, but what does it help for in our situation? Yeah, when we know which layer is executed at the moment at a singular queues, we can detect which state we can write to the KVM run struct to circumvent those issues. And yeah, this is so now this should work like that the next time. Okay, our takeaways. Yeah, for us it was the first really large project after years which we don't work with KVM, and because we have worked with other virtualization APIs. So what our finding was is that for us it was a bit hard to find the documentation, or we even have to look up Qemu and KVM source code to understand what actually is going on when we ported VirtualBox KVM to this backend, the KVM backend for VirtualBox. And yeah, also there are some assumptions we made which are violated. what I mean is that marking unchanged values as dirty and just writing it back, it should be a no-op from. That was our assumption, but yeah, this wasn't the case. Also, we had another with the Lepic code. I haven't detail.
Yeah, so if for debugging, you just call from a random thread KVM get Lepic. This leads to interrupts being lost, which is super unintuitive. So you would assume that if a IO control is called get some state, that is actually not mutating that state, but this is not true. And this has made some debugging sessions more complicated than they could have been.
Yeah, but yeah, we want to improve that, I guess. So a question to the might be afterwards, after the session, how can we improve this? Can we write some documentation for others? They want to change, they want to add the KVM to another VMM, or even is there a way to simplify the APIs? So yeah, let's talk. Okay, but yeah, I told now we have the solution for Windows and it works pretty well. Also, the performance is competitive to native VirtualBox. We just tested it against Qemu right now. No, we don't. And yeah, what we support is we have tested it on AMD laptops, AMD servers, and Intel CPUs. The nesting works for Intel, and we have also implemented a Virtio-gpu and Vfio support in VirtualBox, so that we can pass through Intel Sr-iov-enabled GPUs up to the Intel Xe GPUs, especially from Alder Lake and newer. So yeah, also almost all VirtualBox convenience features like shared clipboard or the guest integration itself works with the KVM backend as well. There are some minor integrations that won't work, but we are open if someone gives us the money to help with the development to enable this as well. So now I give back to Julian.
Thanks, Martin. Yeah, so if you're interested, we blogged about our endeavor, so you can go to our company blog. There are a couple of blog posts. If we do something else, we'll probably blog more about it as well. This has been actually pretty fun, the whole project. It's also nice because we can write about it and it's not confidential or anything. Yeah, this was already it. Yeah, okay, this was already it. So in summary, we have a patch set for VirtualBox that adds a KVM backend to it. It just works. It's really nice. I use it as a daily driver. So if I had more hands, this was the wrong one. If I had more hands, I can just click on it. Thanks. You see that this also is a PowerPoint that runs in VirtualBox on my laptop, and you can also just next to it start some Qemu stuff in it, so it works. It's all on GitHub. You can find it on GitHub. It has a sponsor button, so at the moment we do this for our own entertainment and for our own usage. But in case you find this useful, or one of your relatives, if you have some relatives that need a user-friendly virtualization tool, definitely use it. Other than that, the KVM API works, but is a bit for the brave. So if you come to it not knowing the details, be prepared to read Qemu code, to read KVM code, try to understand it. I think we still haven't understood how control register stuff works in nested virtualization. I think Sean does, and I'm very grateful for it. We're super happy to be constructive about it. So we're not. We understand where this comes from. It's all, I mean, historically grown. But we're eager to help in any case that people point us to. For using this, we have packages. There are some super motivated maintainers that have packaged this. You can use it on NixOS, Arch, Linux, Gentoo. There's probably some Ubuntu PPA somewhere. And there's commercial support if you need it for VirtualBox, for Cloud Hypervisor. We do Nix and NixOS stuff, and of course, testing. Yeah, just get in touch with us. And this is it from the presentation, and now we're happy to take questions. I think we have quite some time for questions.
Can you elaborate on the non-atomic PIR to IRR sync? What's what part of it is non-atomic that you don't like?
There's some hidden state that gets synced to the interrupt to the IRR register. And if you call this from a different thread, and on another thread there's an interrupt signaled, I think there's a chance of interrupts being lost. And this is, I mean, in a sense, this is okay. That this happens because in the hardware it also works like this. You cannot just fiddle with the register atomically, but I think this should be spelled out in the documentation somehow, like don't call this from another thread. If you want to know more details, I can connect you to Thomas I mentioned before, who's probably happy to explain you the details.
Can you post on list the gory details of exactly what is broken or what you think is broken?
I think it's not broken, it's just very surprising that this happens.
Even if it's just surprising, like if it's broken from the perspective of you read this and this is idiotic from what you think should happen, just post on list and we can go from there. And
awesome, yeah.
I mean, worst case scenario, we add documentation and say, yeah, here be dragons, this is a stupid API, but...
Yeah, sure.
When you said that you had to look in the code, that means that the in-kernel documentation was in no way sufficient or useful for you, or?
Yes. So I think to know how to use the interrupt code and the event injection stuff, you just have to read Qemu code and see what Qemu does. If in doubt, do it like Qemu and you're happy.
Because that would be the natural place. If you really want to add documentation, that would documentation word that folder. But or at least tell us which parts of this documentation sucks. And I know a lot of things.
I think the most valuable would be overview documentation. So like, hey, you want to write a VMM, you will have to inject interrupts. Do this, use these 5 I/O controls, ignore all the other stuff that exists, but do not touch it.
So some kind of hypervisor for dummies in 10 steps, whatever.
Yes, and probably it exists somewhere, the reference code, and it would be nice to point people to it. Yeah. I think for the nested virtualization semantics, I think I would say from the documentation, we were just lost. And I'm pretty sure that for VMX, all the VMMs that are out there don't handle this correctly in edge cases.
And second question, when you said about the control register mix-up, was that using the syncreg feature, or what was? Where did you have the dirty flags set? Was it syncregs?
In the KVM run sort. Yes.
Okay.
Yeah, the dirty regs problem was they were setting the sync regs, telling KVM to refresh the CRs on every KVM run. But they were doing it using the L1 values. And so if you took an exit to user space while L2 was active, then they jammed in L1 CRs into L2 because they were setting the flag all the time.
The question is this something that we should fix in KVM?
No, this is user space, don't shove L1 state into L2.
Yeah, but then the question was, how do you find out that it's actually L2? And if you actually want to change something, how do you get control back if L2 exits to L1?
So I don't know when that might be. I don't know the details of x86, but on the SR90 part, when you exit user space, you always get the host register parts, and the guest values are completely hidden away from user space.
Yeah, the problem is x86 doesn't have a clean split where you have virtual registers for things. Especially when you get into nested, you have to, the things allow you to just save out what the state is. And it doesn't, there is no, it's resident in memory somewhere, but that's not the CPU state, and all of KVM octals work on what the actual current CPU state is. And so when you read out registers, when you set registers, you are setting for the current state, and that happened to be L2, but you use L1 values and you blow up. And so really it was the lack of a way for user space to know L2 is active without having to make another syscall just to know L2 is active. So chuck a flag into the run structure.
In that particular case, you were running the sync regs, right? So you just use the KVM run synchronization registers. Why was the wrong CR4 registers in the sync regs when you got out into user space? At that point, you should have synced the level 2 CR into your in-user space representation, and then when you go back, you can set it dirty as much as you want, but it would be the dirty value of L2.
I think we should talk about it offline, but we just wrote back what is in the CR4. We just marked it dirty, so we didn't change the value. It was just the value that was in the KVM.
They weren't setting the, no, the user space was broken because they were just setting the sync reg bigs. They weren't actually refreshing the values that were in the KVM run fields that KVM was consuming. They were just setting the bit. So the way Qemu does this, Qemu doesn't, I don't even think Qemu uses set regs or sync regs. They just do all the octals. But the way Qemu does this is it keeps track if anything in Qemu has dirtied CPU state. And so the only time that Qemu actually sets CPU state is when it needs to. This was setting it every time because it was cheap, and then you shoot yourself. With the caveat that Qemu also doesn't get this right, and you can reproduce the same issue.
SyncRegs should go both ways, right? SyncRegs also synchronizes them into the KVM run state when it goes up into user space.
Yes, they are in there. So you see the correct CR4, and if you mark it dirty, then magically the wrong bit pops
up. You probably just stumbled over a bug where the push to user space didn't work correctly.
So maybe a different answer here is that the complexity of x86 is not really reflected in the API. So in other APIs, you can just set the CR4 reach shadow yourself, and it's the VMM's responsibility to set something sane in there, and you have all the complexity exposed to user space. And in KVM, it's a bit difficult to figure out how you should hold it.
Maybe a last question. Is there any chance or plans to get something back to the VirtualBox project or that code where you got your initial code from?
I think this is up to Oracle.
Which means no, maybe?
This is up to Oracle.
So the VirtualBox project is not too actively maintained by Oracle. So is there any plan like you have this KVM backend like to maintain further, or what is your future plan?
So at the moment we will maintain it further. We don't have a lot of resources to spend on it. So as long as it's just rebasing it to the newer VirtualBox version and sending it through our test stack and publishing a new release, we're probably going to continue this for a while. If too much changes in VirtualBox and we would have to touch bigger parts of it, we have to see. So because at the moment there's not a lot of commercial interest in this, so basically doing this as a side project.
Thank you.
Thank you.
So today I'm going to do a presentation on Qemu support for the Windows hypervisor on ARM, and more broadly, how to leverage extensibility in the Hyper-V stack. First of all, I'm an engineer at Amazon EC2, and my opinions in this presentation are mine. So for the agenda, I will start by saying what's going on in WSL2 and the Windows subsystem for Android. Then after that, I will talk a bit in detail about the HCS stack which powers this. And after that, I will talk about the Windows hypervisor platform, which allows outright to run another VMM. An overview of the stack. So there is the host compute service, which is running as system. There is also the VM worker process, which has the core VMM that's running fully sandboxed. There is support for out-of-process device emulation via VM device host, and that runs in a different privileged context, and it's invoked through COM. And the WSL service itself also runs as system. For file sharing between the guest and the host on WSL, that's powered by Virtio-fs. There is an 8 GB shared region for performance. And it can be initialized directly via HCS API so that a third party needing to use that device on their own VMs don't have to deal with custom device emulation. And for Windows guests, the whole Virtio-fs infrastructure is not used, but VSMB instead. So there is a WSL device host. This is an emulation layer for some Virtio devices, notably Virtio.net, but no Microsoft product ships with that. There is an implementation of Virtio PMEM. And this component uses VM device host, but it does not leverage VM Virtio DLL, which also runs on top of VM device host. Then there is a bit of a surprising one for the Windows subsystem for Android. So for the Windows subsystem of for Android, instead of implementing the WSL2 Vgpu architecture, a different path was chosen, which was implementing Virtio-gpu with a GFX stream. At this point in time, a Windows subsystem for Android is officially deprecated. So now about the host compute service. There are 3 separate types of Hyper-V partitions that somebody can create on an off-the-shelf Windows installation. There are regular Hyper-V virtual machines which are stateful, with the state being stored inside of the Hyper-V services. This flavor of Hyper-V VMs is only available on professional SKUs onwards. So if you have a home edition of Windows for wide deployment, you can't use the deployment option. Then there are HCS virtual machines. So HCS is available on home editions, so it's available pretty much across the board, but it has close to no good public documentation. And there is the third option, Windows Hypervisor Platform, which allows implementing a custom VMM outright. So this, with the last option, you can actually use Qemu. HCS takes a JSON with virtual machine settings, when running virtual machines because it also supports process isolation containers. Nanabox is a third-party VM launcher tool which uses the HCS APIs. It was a good starting point because it allowed to easily create an HCS backend virtual machine. Now let's talk about Hyper-V out-of-process device simulation. So for this option, COM is used to start the device simulation process across a different security boundary. But you don't have to implement all that stack. So if you run as administrator, you can skip implementing most of this. Then there is VM Virtio, which is a small layer on top of VM device host implementing Virtio-specific infrastructure. It's undocumented, but the Virtio-FS implementation is built on top of it. Then let's talk about the core component here that is going to be used from that third-party process, which is a VM device host. For the config space, it's fully emulated within VM device host. For the bars, it's a doorbell design where it's possible to trap writes to part of the bars. And then we get a notification event when the guest writes to that bar. The write is not done at that point. So if you do a write and then you try to read right afterwards, the write will not be reflected. The device simulation layer, which is controlled inside of that third-party process, might choose either to reflect that write or not reflect it, which means that it's suitable for implementing something like Virtio or NVMe, but you can't really implement something like ASCI with the doorbell design. So for supporting it in Qemu, I prototyped the Qemu OOP device binary. So running it as administrator, just that hashing. So would it be worthwhile to continue on that route? I don't really know. And if we are going also to support out-of-process arbitrary PCI devices on Linux, to which extent should it be arbitrary? For example, making writes to bars with doorbells that are async allows to not block the VMM process all the time. So it can be critical from the performance perspective. Now about Windows hypervisor platform. So it's an API to support third-party VMMs on Windows without having to run on top of Hyper-V. Only one VM is allowed per process. So let's say you are trying to make something like VTLs. That's not going to work with this API if you try to implement it fully in user mode. And by the way, there are VTL mentions all over the place in the Windows hypervisor platform API. But VTLs are not implemented in Windows hypervisor platform. It's in preview for ARM64 since Windows 11 version 24H2. And on x86, it has been there since quite a while, and it's implemented on VirtualBox. And it's also implemented in Qemu. So for this one, documentation is not ideal either, but it's not too bad. So for the gig state for Windows hypervisor platform on ARM64. So as of the latest public release, which is shipping on Snapdragon XLE devices, there is no way to move the gig MMIO address range to another location. it's fixed at the address for which a regular VM runs, which means that an off-the-shelf QEMU mvirt machine model is not possible to support in that configuration. Which means if we want to support that configuration at this point in time, we have to do a specific Hyper-V machine type. It's addressed in a pre-release build, and it actually works on that pre-release build, but the SDK for that is not currently publicly available yet. And it's a Geek v3 without ITS support. It implements a Geek v3 without ITS, and there is no way to support a third-party interrupt controller for it. So there is no option to use a user mode IRQ chip. So on the hypercall side, the Hyper-V hypercalls are always exposed. And there is no way, for example, to trap SMCs so that they get handled in the custom VMM. So on a regular full-fledged Hyper-V virtual machine, there is Virtio support available, even as an ITS is not available, because inside of the Hyper-V VPCI code, there is an IRQ chip implementation which supports that use case for MSI. So the consequence currently is that Virtio devices are not functional in the current state of my port. Windows Hypervisor platform has VPCI specific APIs, but I didn't start using those yet at this point. So on the future plan side, I was planning on getting MSIX working. Maybe those VPCI APIs are the solution. I didn't quite look at those in detail yet. And perhaps writing an M-Hyper-V target, which is almost the same as mvirt, but with a GIC in a different address range, so that users can start testing this today and publish an RFC at some point. So that's it, and I think I went way too fast. So any questions? Oops.
For adding the Hyper-V machine at the end, can you just use the virt machine, and if the hypervisor is Hyper-V, you just change the MMIO range for the geek, so we don't have to maintain another machine on QEMU?
I think it would be possible, yes, but it wouldn't be very standard. So you would get a different representation of mvirt depending on the platform on which you run on. I'm not convinced that that's a great idea.
Uh, 24H2 is kind of almost now. So is it really worth to upstream the new machine type instead of just a little bit waiting for the SDK to be published?
So 24H2 currently has this implementation, and the Windows Insider preview has the new fixed implementation. And I can't say myself on when this will be available on 24H2. So no further questions?
Thank you.
Okay.
like this was way, I don't know about them, but certainly way beyond my expectations, both in participation in depth of technical content and having fun as well. So also thanks to the Qemu committee that some of us are here in with two different hats. But thanks also to the Qemu committee and Conservancy for allowing to handle the finances of the conference through Qemu. That has helped a lot and made some things much easier. First of all, if anybody of you have something else to say, go ahead. At least one, otherwise I make like...
Well, thank you, Paolo, for all the work you've done in getting this organized.
Something else.
If we're going to say thank you to Paolo, we should say thank you to the local Red Hat team who've done the AV and the organization.
Yeah. So I also want to say thank you to all of them also for the help in the organization, because actually it wasn't not entirely done all by me. Maybe I had like some more regular things, but the help of everybody was useful. So thanks to everybody here as well. And some of you may remember that in the beginning there was this idea of having this KVM Forum in Milan, which was shelved for various reasons. It's still not 100%. Maybe we find some other occasion to co-locate, just like we did with Plumbers this year. Probably not Plumbers next year, but anyway, we may find some co-location opportunities, but if not, it's quite likely that we'll have a KVM Forum 2025 in Milan in September. So see you next year.
At the risk of sounding cheesy, I would like to thank you folks, because without you, all of this wouldn't happen.
And also, last but not least, or maybe not last even, I would like to thank the sponsor, not really for the contribution, but also especially for trusting the organization. I think last year we showed that we could organize KVM Forum alone, and this year we showed that we could organize a great KVM Forum alone.
Numbers.
Oh, numbers. Numbers is 200 people. And
compared to last year?
Well, yes. Okay. Numbers are basically the same as 2022, which is already great. Compared to last year, about 30% more people that wanted to come to KVM Forum, and 50% people that actually came to KVM Forum. So last year we had 150 tickets and 120 people. This year we have 200 tickets and 180 people. That's it.
See you next year.
See you next year.